All right, we're live. For those of you who don't know, my name's Robert Bankston, K4AL. I am the president of AMSAT, and I want to personally thank you on behalf of AMSAT for coming today and helping us to share in the experiences of amateur radio in space and see where we can go next. We've got quite the schedule from both in-house and inside AMSAT, as well as what's going on elsewhere. So thank you for attending. I hope you have a great time. We are going to, I guess we're scheduled from today till 5. Then we have a break for dinner. And then at 7 o'clock, we're going to get together in a social, which will be over here on my right, your left. Just keep walking past the booths until you see a place called The Social. We've got some hors d'oeuvres, drinks, that sort of stuff. And there's going to be a live auction. So thank you again for attending. Enjoy your time. I encourage you in breaks and sessions and elsewhere to engage in conversation, and usually some of the best stuff about AMSAT comes out in the side discussions. So thank you so much. Enjoy your time.
Thank you very much, Robert. I am Zach Metzinger, N0ZGO. I will be functioning as the Master of Ceremonies, your MC for today and tomorrow. As Robert mentioned, we have a lot of great presentations. Please, connect with everyone you can. Also at this time, if you would make sure your cell phones are on silent and or vibrate out of respect for our presenters. Our first presentation today is by Jonathan Brandenburg, a survey of small satellite propulsion systems. So a warm round of welcome for him, please.
Good afternoon, and thank you very much. One of my roles here at AMSAT is the Assistant Vice President of Engineering. And as a part of that role, I do have the opportunity to work and manage the Ascent program. And so it's my pleasure today to introduce a new Ascent endeavor that I think will be very interesting to our membership and to our volunteers in engineering as well. So I am here today to talk about small satellite thrusters that are appropriate for CubeSats or what the industry considers small satellites. And I do need to remind us, I suspect, that our idea of a small satellite is sometimes different than the industry's idea of a small satellite, but it does range anywhere from your CubeSat footprint up to your, Volkswagen Beetle or even van size can occasionally be considered a small satellite. But what I'm talking about today are primarily the technologies that are applicable to the thrusting, the maneuvering, the orbital changes for true small satellites in our vernacular, being the CubeSats. And I'd like to talk a little bit about why, and certainly you can question these, but over the past several years, I would have to imagine that we've heard a lot about the requirement for deorbiting of satellites, the orbital debris problem, the pending and new FCC regulations around deorbiting your satellite. And in fact, I think we have seen in the news recently the first fine for an orbital debris violation. Correct me if I'm wrong, but I think that was Dish Network. Now, to be clear, this was not a substantive fine. This wasn't a backbreaking fine, but this was the test to show that the FCC could levy fines when they so desire for the violation of orbital debris rules. At least that's my interpretation of that relatively small dollar figure. But I also like to point out that, we kind of had a sense that debris mitigation was going to become an issue, become a factor in our satellites some years ago, and we've been working toward understanding how to deorbit on command. But what I'd like to point out is I'm also beginning to hear in conversations with organizations like Space Force and even the FCC, maybe some hints that the requirements will be evolving into the future as well. No rulemaking, no official on the record statements, but beginning discussions about how satellites will both have to report their own position accurately and not depend just upon ground-based radar to find them. But also the idea that we're going to have to be able to maneuver to avoid what we euphemistically call conjunction events, or and also at the same time to coordinate that maneuvering with a central authority. Now, to be clear, Space Force is very clear that they're not necessarily that authority. They're not trying to manage it. But they have mentioned to me the need to begin coordinating maneuvering events. And so this idea of small satellite thrusters is becoming increasingly applicable, I think, to our work looking forward. And that's part of what the Ascent program here is to do, is to look forward at technologies and evolve new technologies for use in our future launches. So that's why I'm talking about it today. We have a GNSS program that we briefly discussed for flying on Golf T. We decided that was not mission critical for Golf T, and in fact may have been an additional technical burden on the staff, perhaps. But I wanted to at least continue that work, so we're spinning up an Ascent-based GNSS evaluation for payloads on our satellites. Now, Golf T is going to be flying an ADCS, and I'm stealing a little thunder from our VP of Engineering, wherever he is sitting or he's probably writing the presentation right now, knowing Jerry. But we will be flying an ADCS on that from CubeSpace, at least at the current time. That's definitely the plan, and we've begun development toward that. But we really haven't had any sort of thruster opportunities. So I went and did a little research, and I went and had the opportunity to attend the Small Satellite Conference in Logan, Utah, where I saw a very cool product demonstration. So cool, in fact, that it looked to me as an opportunity for us to start, I guess getting excited is one way to look at it, but also beginning to think that it's truly something we can accomplish, and not in the distant future, but in the near future. We can accomplish maneuvering flight with our satellites going forward. But before I go into some of that, I'm going to take a brief moment to talk about the different kinds of technologies that we tend to see in small satellite thrusting. This was, after all, a talk that's supposed to be about a survey of small satellite thrusting technology, so let's go ahead and do that first. Some of us in this room have recently learned or relearned or already knew about the existence of this document called the State of the Art of Small Satellite Technology. This is a document that's published by the Small Satellite Virtual Institute. I'm missing an S because it's S3VI, I think. But a NASA-based institute to support the development of small satellites. On an annual basis, they release this report. And this is a long report that's listing dozens, hundreds of technologies that are applicable to small satellites, including CubeSats. And it ranges from attitude control systems to data processing systems to structures to communication systems and thrusters. So I shamelessly stole this slide from that report. And what I like about this is this nicely shows the categories of different kinds of technologies that are available for, quote, small satellites. You have your traditional solid motor, like your SRBs on the shuttle would be a big example of that, but certainly smaller solid motors are certainly plausible for small satellites. You have your traditional hydrazine, your hypergolic type fuels as well. And then more recently, especially in the hybrid and the mono biprop range, we've started to concern ourselves with so-called green propellants. And it's not because we completely are so worried about the environment, although we are in many cases, but we're more worried about the safety of personnel and the cost of handling those propellants. So a lot of these green propellants are green more because they're safe to handle, store, work on your satellite than anything else. There's also on the left side there your electrothermal and your cold warm gas. Those are basically your pressurized tanks of air that you just spurt out your nozzle. Sometimes you'll heat it up, but you won't heat it up to extreme temperatures. And then on the bottom right, you have your variety of electric thrusters, and I can talk more about those if there's questions, and I have time at the end. But as you can see from this graph, there's different groupings, and the vertical axis, the y-axis, so to speak, is really kind of the average or maximum thrust for that kind of technology. And being a logarithmic scale, I think that's the right term, you can see, of course, that solid rocket motors are extremely powerful. On the other hand, on the x-axis, the specific impulse, in layman's terms, because I'm actually a layman in this context, so I don't mind saying that, the specific impulse is basically the efficiency of the propellant based upon the weight of the system. It's just a really easy way to talk about it. And in many systems, that's based upon the exhaust velocity of whatever your propellant is going to be. So if you have an extremely fast propellant going out, which is often the case with electric thrusters, then you're going to have a very high specific impulse. So it's in a measure of efficiency is the way I'm going to describe it. And for the experts out there, I already apologize that I am simplifying it beyond the point of reason at some point. But there are several different kinds of electric thrusters. Your Hall effect are the ones that we've seen a lot of. I suspect that most of the NASA interplanetary missions that we've seen, even though I didn't do the research to say this, but from what I know, most of those are going to be Hall effect type thrusters. They're fairly large, they're fairly power hungry, but they're very reliable and they're very effective at what they've done. And they rely upon, well, Hall effect, the magnetic electric field is about my limit of knowledge on that one. But there's several others. Electrospray is another one that's interesting to me in the sense that it uses either a liquid or a solid propellant that it melts down real quickly, and using an electric field throws the exhaust out the nozzle. There's several different vendors for that, and it's a really affordable technology, and it's a moderately simple technology as well. But what I'm talking about today is the very bottom arc of that, which means in some ways the lowest thrust, but it has the benefit of being a very, very simple system, a very simple technology. And that's going to be the pulsed plasma or the vacuum arc. And what these will do is these will basically use an electric arc to ablate the fuel, ablate the material which becomes the fuel. And so there's a variety of fuels that are used. You'll find some light metals, but oftentimes you'll find some high-tech plastics that are used as an ablative material. So it is my pleasure today to demonstrate such a plasma thruster here in this room. Before I go to that, though, I am going to at least slow down and pause and see if there's any questions that I can answer up to this point about the general concepts that I'm getting across today. So the question is, what is the material that's typically used with a vacuum arc? I haven't seen a typical material, but I think, and I'm pulling this from memory, so if I get the initials wrong, like a PTFE type material is one that I've seen is very common in that technology. But that's the only one that I found specifically referenced.
And then how long will that arc last?
How long will that arc last? Now, it doesn't provide a lot of thrust, but it can provide thrust for a relatively long time. And you're about to ask me a question I can't answer in a moment, so let me tee that up before I answer your question. The thruster nozzles that I have here today, which are air-safe thrusters, they fire in air, will typically fire easily 10 to 15,000 times. And when I say fire, let me set your expectations a little bit here. There's not going to be a 6-foot gout of flame spurting across the floor. It's going to be more of a pop, 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 or pew, 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 if you so prefer. So it will issue a lot of pews for a long period of time. And when we're working, of course, as you know, in a weightless environment, especially with a low mass spacecraft, that can actually yield a fairly substantial orbital change in orbit, such. As I repeat my word orbit again. All right, any other questions? Good ones. Hold on, we're going to have a wandering mic, Kip, so we're going to use the mic real quick here, if we may.
Is there something that burns or something that is consumed?
Is there something that burns or something that's consumed? I'm repeating your question anyway, even though you're on a mic. The answer is yes. It's not burning. That's actually key for most of these technologies. The only ones that are exothermic in nature are going to be your solid motor hybrid, mono biprop type things. But there is definitely a consumable in all these cases that I'm talking about today. In this case, it's that center core. And I will invite everybody to look at this once I get it sealed back up again. I'm happy to hand it around the room as long as you don't throw it on the floor or play catch with it or something. Does that answer your question, Kip?
Yeah,
How heavy?
is that consumable?
How heavy is the consumable? The consumable is actually fairly light. I don't know the answer to that. You're getting into those I don't know answers. But it moves very, very fast because of the plasma arc effect. Amir, yes, sir.
Yeah, doesn't any of this, I mean, don't we have to have like attitude control?
Don't we have to have attitude control?
Yeah,
Yes.
to be able to use this at all.
Yes, we absolutely do, and I may have glossed over that a little bit, but in addition to the location information of a GNSS project, I briefly mentioned the ADCS on golf, but I didn't exactly make that connection, which says in order to use thrust, you have to be pointed in the right direction, which is where the ADCS does definitely come into play. You're absolutely right. I think Tom may have had a question back there. That was Tom's question. And I'm happy to take as much time as y'all will give me since I had 14 extra minutes, but I'm also happy to go on with the demo as well. So we'll go down that route. Oh, wait, we have one more. Go ahead, Lou. Mike's coming around to you.
My question was that the PTFE, is that making fluorine gas or anything toxic?
Does the PTFE fuel make a toxic gas? The answer is very plausibly in flight, but I don't have that problem. I don't remember what my fuel is, but it is actually non-toxic. That's part of the reason what I'm showing you today is actually not flight ready. Not only is it specially designed so it arcs in air and doesn't short out things, but the fuel and the housing is not space rated either. Alrighty, I will need the mic because I'm going to be moving over here. And how's my spacing and volume on mic? All right, good, good. As I noted to our AV engineer, Brad, I do have a tendency to yell in a group setting anyway, so he's also probably adjusting the volume. We'll deal with that. All right, so what I have here today is a development kit, and I want to say very specifically this is a development kit from a company out of South Africa called Hypernova Space. This is called the Lumen SDK, and the stated reason for Hypernova Space developing this is because they wanted people to begin experimenting with plasma arc technologies. This is an open source and open hardware based platform. That's already true. It's licensed using a CERN license, which is something resembling a copyleft license. So you have to share your changes if it's going to go outside your organization. But he's even, the company manager, Jonathan, who's brilliant, Jonathans are brilliant, has mentioned that he's willing to host a seminar on how to develop our own nozzles and fuel systems. So he's very willing to share, presumably if we help advance the work. What else did I want to say? I think that's it. So we're going to go ahead and continue with a simple demo, and this will be going on the screen. Let me go ahead and show you what's up here before we shift it to the screen. We may end up switching back and forth. So I have here a very simple GUI that has been developed to control this from a development standpoint. And what we'll be seeing here is I'm going to be firing thruster number 1. You can see thruster number 1. This particular device has 4 thrusters, numbered 1 through 4. 1 and 2 are dummy loads. They basically dissipate as heat and flash a little bit of light when they fire. Thrusters 3 and 4 are actual spark gap thrusters that will ablate fuel, and they're the ones that make the more impressive pop-pop sound, if I'm easily impressed, I suppose. So what I like to do is I like to go ahead and first retrieve the telemetry, which you'll see when I come back to this screen, and then I'm going to fire the thruster 1 5 times, about 2.5 seconds apart. So with that, let's go ahead and switch camera over. Oh, I'm streaming? Can we put it on screen, or do we have that ability? We don't have the ability. Okay, that's fine. Watch for flashing lights here, if you can see it. So I'm going to go ahead at this point and power on the system, and apparently I forgot to open the port first, so let me start all over again. Da-da-da-da-da. There we go. We're going to open up the port first this time. And then what I'm going to do is I'm going to go ahead and retrieve the telemetry. And what the developer told me that I should be doing here is making sure that the voltage is set properly for the power that we're driving through. And in this case, I'm not turned on. So if I power on, read the telemetry again, I'll see that my set voltage is 39.8 volts against a nominal commanded 40 volts. So my power systems appear to be working properly. The thruster is probably ready to fire. I'm going to go ahead and change this to a 10 count. I'm going to go ahead and change it to 500 milliseconds because otherwise 1 second between pops of light seems like an eternity. And when I fire, it's going to fire relatively quickly, and I need somebody to tell me if you are indeed seeing a light there. It's a dissipated light. So 1, 2, and 3. And we're seeing the flashing light. That is a simple dummy load. It just happens to flash a little bit of light while we're at it. Now what's interesting about this is if I go to the waveform, I actually see the telemetry captured during that run. And you'll see that our voltages reached as high as, say, 60 volts at peaks. And the current during those peaks was roughly 40 amps. So you can do the math and see for brief periods of time the amount of power that was dissipated by this system. It's got some internal capacitors that it charges up to store that. At some point, somebody's going to ask me today, what are the power requirements for this device? I sort of know the answer to that, and I'll show that to you proactively. So that's that. Now, what we also can do, and what I'll do this time, oh, we have a question. I'm sorry. Is that in microseconds? Oh, you mean on the waveform? That is in microseconds, yes. Thank you for asking. That is in microseconds on the x-axis. How efficient is this? You're going to hear me say a lot of times today, that is forward work, which means I don't know. But that's also part of the reason I'm standing here today is, again, we've got these SDKs. I bought 2 of them. Why buy one when you can buy 2, right? You know my motto. But what I want to do is I want to get this into our hands of our engineers, and I want to start researching and answering those types of questions. I've had one of our volunteers already volunteer to do some modeling of the thrust vectors and so forth. It'd be interesting to have somebody looking at it from an engineering standpoint as well. All right. What we can also do is we can also load pre-programmed systems. And I'm going to go ahead and load thrusters 1 and 2. What this will do is this, after a 5-second delay, which that part's weird, but patience. After 5 seconds, it'll kick off this program and it'll flash both thrusters 1 and 2 10 times. And I hope it works. Okay, 5, 4, 3, 2, 1. Ha. The thing about live demos, you're always happy when they work. I'm glad they're working. So all I did was flash lights back and forth. Now you'll notice, by the way, this waveform was captured in this case, and it starts to actually clip a little bit on these thrusters. We're actually driving more power through than these sensors are capable of receiving. But when I change my firing sequence to fire 3 and 4, which is what I'll be doing now, this is where you're supposed to ooh and ah, because something very exciting happened in about 5 seconds. There you go. Pop, 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 pop. Now, I will put the cover back on this and hand it around, and what you will actually see is you will see burn marks in that center fuel rod for all the times that I fired this thruster, and that's what happened there. Not a lot of thrust, but continuing thrust for a long period of time will give us some ability to maneuver our satellites. And again, my objective here today is to show off something that I think was pretty darn exciting, an accessible SDK that we can get our hands on for developing electric thrusters. And at the same time, I wanted to make sure that we had the opportunity to engage our volunteers in that effort. So now here's we get to the point of I can't answer most of your questions. Yeah, go ahead, Bill.
Hang on just a second. There we go.
Is that voltage of up to, what, 60 volts or whatever it was, is that both the arc voltage that's vaporizing the material and the accelerating voltage, or is there another higher accelerating voltage to accelerate the plasma out?
Can you read the top of that slide for me?
It's a good thing to investigate, though.
Yeah, I'm honestly not sure about that. I just received this a very short time ago, and haven't delved into it, but I would love to engage somebody, you, including the YouTube you, to join our team to begin investigating these capabilities, answering these questions. And to be clear, I'm not convinced this is the right technology even, or the right thruster for our use. But we won't know that until we start investigating it. So I want to start investigating it at this point.
Just a quick point of operation here. When you have a question, please raise your hand. Wait for me to bring the microphone over so our YouTube viewers can listen to it as well.
So given the current state of the technology, how much real estate would this take in a CubeSat? And how efficient, how much is that going to impact then your design of your CubeSat when you add this?
So Barry, I'm going to answer two questions, one that you asked and one that you didn't ask. The size of that, as you can tell, is about 3/4 of a U, and that is approximately the volume that would be required. I did promise to answer your power question, which I'll come up later. The question you didn't ask that I want to answer, though, was cost. Did I ever discuss cost? I talked to the manufacturer of this, and this SDK costs about $3,700, which is not a super scary sum. It's not something I'm buying out of my own budget, necessarily out of my pocket, but it's not scary for us to investigate. I'm told to expect that the flight model will be somewhere in the range of about $15,000 for a flight thruster with 4 nozzles, so that's not too bad at all. Andrew, I believe you may have had a question.
Yes. Have you had time to quantify RFI, EMI, EMC concerns? Yeah. No, I'm just curious because, you know, it looks like a spark gap transmitter.
It very likely is acting as a spark gap transmitter, no doubt about that. I have not characterized anything of that nature. I really have little technical information about the capabilities, like how much thrust even does this generate? That would be a very natural thing for us to have to answer. I'm looking forward to somebody answering that.
And a question about that question is, what type of delta in orbit could we actually expect?
And that the delta in orbit will depend entirely upon the mass of the satellite and the thrust available from that thruster. I don't yet know enough to answer that.
Well, I'd just be very curious to see what this does to a linear transponder. You know, straight
while firing,
you know,
does it do anything fun? There may be some challenges associated with that. Let me go ahead and pull up one slide here. I'm going to go off mic for a second and not talk.
Did we have another question on the other side of the room? Nope.
Because at some point somebody would have asked me about power. Those are the power requirements for this particular SDK. The 12-volt line is the one driving the actual arc. So we're talking about 3 amps or more on 12 volts to drive the actual thruster itself. The rest are the power control, are the control electronics and the CPU, I guess is what I'll call it. All right, great. I appreciate your participation. Any more questions before oh, Barry may have a question for me.
Okay, simple question. SDK.
Thank you.
SmallSat development kit, maybe?
Software development kit, but we tend to overload it a lot to mean any sort of development kit, to be honest. We can call it a system development kit, as Badale suggests. Lou has a question, I believe.
Are there any user hazards, like handling hazards, or
are there any
potential to get shocked or anything like that?
Yes, there are. I was specifically told not to put my hand or face within a foot of that when it's firing. There is a chance it could arc and ground through somebody, so we do have to be careful of that. I also removed the faceplate, and that's because if I'm ablating the air gap thruster into that faceplate, it doesn't hurt anything, but it'll eventually scar and obscure the faceplate so you can't see into the device anymore. That's why I take the cover off the front. So yes, there are definitely going to be safety considerations involved in using this. Did Will get the mic? Yes, Will.
Yeah. Has anyone considered using differential thrust for attitude control using something like this?
Has anybody considered using differential thrust? The answer is absolutely. I myself have been part of a team that has considered using FEEP thrusters, which is a form of electrospray thruster, to do differential attitude control, so I know it's possible. There's no specific reason that the nozzles have to be associated with the power electronics. Those nozzles are actually very removable. I told you I bought 2 kits. I did. I've already had to return one of the nozzles because it arrived to me non-functioning. I just pulled it out with a gloved hand just because I'm safe that way, put it in an envelope and sent it off. So it's very easy to replace these components. I've now been speaking for 30 minutes. I don't know how much time I really have, but if I have more questions, I'm happy to answer them.
You've got about 15 more minutes if you want it. Otherwise, you don't have to. Any other questions for our
Was there a question back there? Was that a question? Okay, no question. Well, in that case, thank you very much for allowing you to open today.
Thank you very much, Jonathan. We appreciate your presentation today. We've got just a tiny bit of reorganization on the laptops, so bear with us for just a second here. Do you have everything?
I don't know where the slides are at.
Oh, yeah, they're somewhere.
Where are they at?
So you're done? So are you going to start? Yeah, we're going to start with Jerry's.
Where's Jerry's at?
Okay. So up next, we'll have the VP of Engineering, Jerry Buxton, with a AMSAT engineering update. Is Jerry in the room? Hello, Jerry. If not, I could certainly go first. I'm gonna go ahead and start. I'm going to introduce myself. My name is Zach Metzinger, N0ZGO. I am one of the board members, but I'm also an engineer on the golf program. And I'll be talking today about our aspirations for microwave on golf. So as soon as they get me set up here, I'll start talking. There we go. Let me make sure this thing actually works. There we go. Excellent. Okay. All right. I'm one of those guys that likes to walk and talk at the same time. I hate being up there. So again, thank you all for attending the 41st Annual AMSAT Symposium. And I'd like to talk to you about our microwave efforts on golf. So a quick background, a lot of you may know this, some of you may not, just depends on how long you've been around. AMSAT was founded in 1969. It was the follow-on successor to Project Oscar, which were just a bunch of guys that wanted to put amateur radio in space. And Oscar standing for Orbiting Satellite Carrying Amateur Radio. So we have a lot of successful and some not so successful satellites in orbit. A07 was launched in 1974, which makes it 2 years older than I am. And it's still the oldest satellite of our fleet that is still in operation and can be used. I had to clarify that one. We have over 4,000 members as of the 1st of this month. And we have sister organizations in many other countries. We have some representatives of those here. AMSAT Switzerland, Mr. Michael Lipp. We also have AMSAT UK, David Bowman, which I don't know where he is sitting, but he's surrounded. Oh, there he is, over there. And I don't know if we have anybody else, but those are the two I know who are in person. So it's not just us here in North America, it's everybody. We have had growing ambitions from the start. This is Lance Jenner, this gentleman up here. And that is the first amateur radio satellite right there that he's got under his arms. So those first satellites were the size of shoe boxes. The weight and the size really weren't the driving factor at that point because we were all either on a ride that was high risk, they were testing out a new vehicle, or somebody knew something, or somebody knew somebody, and they were looking for ballast. They were looking for a mass, and it didn't have to just be a lead weight. It could be something useful. But again, we wanted to get bigger, and bigger is better, right? So we kept developing satellites, and the biggest one to date was AO40. It was a multinational cooperation between a lot of different groups. It came in at 4,758 kilograms, and for us English guys over here in the U.S., 10,489 pounds. It had antennas galore on it. We had L-band, S-band, and C, X, VU, and K-bands. And a couple of thrusters. Unfortunately, one of those thrusters was the demise, or actually the fueling system was the demise of AO40. But we had to adapt to the times. So this is the incredible shrinking satellite. So the CubeSat form factor, just as a quick background, a 1U, which is a 10 by 10 by 10, became necessary due to the rising costs of launches. It was enabled by consumer electronics. Everybody wants smaller, faster, better battery life on their cell phones, so it led to the use of a lot of SMT, surface mount technology. And out of this, all of these factors, we got Fox 1, which was AO85, or is AO85, first of the AMSAT CubeSats, with a UHF, VHF crossband FM repeater, coiled antenna wires that popped out, and that was your antenna. And then there were some successors that were launched, AO91, Fox 1B, RadFX-SAT, which is still very usable but can be intermittent. AO92, or Fox 1 Delta, which I've been told just as of this week has started to show some signs of life, which is interesting. So maybe useful. And then AO109, Fox 1E, RadFX-SAT 2, which has sort of a very low power linear transponder and very low power telemetry. It is usable, and people have used it. The telemetry, you got to have a big dish, and that's a big antenna right there. That's Dwinglow. Yeah, Burns has to correct me on that one. There have been some, I guess, a lot of FT4, a lot of digital mode contacts through that, some CW, and I've heard people actually running sideband through it. So you can think of it as the weak signal practice for your antenna farm. Not listed up here are a few that went up, didn't quite work, and now are either inactive or have decayed. But we're glad for their service. Again, getting back to microwave ambitions. So since the earliest of AMSAT satellites on AO7, 2.4 gigahertz beacon, which was never activated because there were issues between the time it was built and the time it was launched. The band plan changed, the allocations changed, and we couldn't turn that beacon on. But it's up there. AO10, the 23 centimeter transponder to the 70 centimeter downlink, and then of course AO40, many bands from 2 to 24 gigahertz. David Bowman gave me a nice picture. Let me use this picture. This is a AO40 setup that was done for a de-expedition to, you'll have to remind me, David. Rodriguez Island. So this was your background, your backyard? Okay, so it's being tested in David's backyard. You know, microwave is easy, sort of. Yeah, the antennas are smaller, more portable. The horn type feeds simplify pointing in exchange for lower gain. You'll get pluses and minuses. Oh, you need a dish. Oh, you don't need a dish. I'm not going to get into that. But the CubeSats, we want to get into microwave as well. So on AO92, Fox 1D, there was something called the L-band downshifter. And that's a 23 centimeter converter. So you're listening on 23 centimeters, and it's actually rebroadcasting that to the 70 centimeter, which is then going back into the transverter and coming down on 2 meters. And what's nice about this is you didn't have to modify antennas. You didn't have to you didn't have to add extra antennas, and you didn't have to modify the transponder. So it was a nice experimental add-on that I think was pretty successful as far as I know. And Burns and Jerry are both nodding their heads back there. So now we come to Golf, greater orbit, larger footprint. So this is the successor to the Fox series of CubeSats. It is a larger satellite. It's a 3U, so you've got 30 centimeter by 10 by 10. It has a lot more stuff inside of it. So even though we've gotten a lot bigger, we're still facing some of the same challenges. We have a couple of really neat things that go into this, and I think Jerry's going to talk a lot about Golf. So I'm really just going to focus on the microwave portion of it. But Golf T, as being the technology demonstrator, the first in the series, headed toward LEO. Golf 1, all those advanced capabilities, after they're tested, they get turned on for general use. And nothing's written in stone. Maybe T works great, and we turn it on for everybody. It's also going to LEO, but possibly MEO. The problem right now that we're facing, orbital debris regulations, and that really threw a wrench in everybody's plans when those came in and said, hey, you can't have these things just up there indefinitely. You've got to move them, you've got to deorbit them. So we're still working through that, but not a complete game stopper. It's just something that changes it a bit. A quick architecture overview, and I'm not going to go into this in detail because, again, I think Jerry's got a lot of this. He's going to go through some of these systems. But just to give you an idea of what we're going to focus on for the next couple of slides, we've got our 10 gigahertz downlink up here. We've got some antennas that go from VHF all the way up to L-band, all the way up to C-band. And then we have a software-defined radio. We've got some other interesting stuff in here that I'm sure he'll talk about as well. So a quick fun picture that was taken of one of the development units. This was done by, I believe this is Don Corrington, right, is AK2S, right, A2KS? AK2S, yeah. So this takes all the antennas, pulls them in, turns it into a matrix that then can be fed into that SDR. And then on the other side, when we're coming out of the SDR at 10 gigahertz, we've got the SSPA, and this was done by Bruce Herrick and John Klingelhofer, I believe, are the two that did this board. So we've got hardware in hand, and it has been tested and seems to work just fine. The SDR is the piece of this that really handles all the microwave traffic. This is based around an E310. May have changed since this slide was created, but that was the one we were using at the time. Downlink is centered around 10.4 gigahertz. The peak power into the transmit array is about 1 watt. On Golf T, this will be primarily used for engineering data. So we don't intend it to have user traffic right away. Now, if it's wildly successful and everything works just as planned, we might have user data coming down on this too. You might be able to go up on 2, or go up on, up on 2 and down on 10, which would be really awesome. But future missions plan to open this downlink for user traffic. We have a multi-band antenna, and the gentleman that did this for us, Kent's multi-band antenna, is a space-optimized design. Covers a whole bunch of bands, all the way from 70 centimeter up to 6 centimeter, and also does GPS L1 and L2, just in case we want to put a GPS on the thing and see where we are in our orbit. It does work best when it's pointed at Earth. He'll say it's omni. Yeah, okay, great, but doesn't an antenna work better when most of the patterns pointed the way you want it, not off into space? So I'm not going to argue with him on that, but that is one of the reasons that we put the ADCS on Golf, is so we can orient ourselves and point the antennas toward Earth for maximum gain. So what does it take to get a golf station or a ground station for golf? It is very similar to AO100. So you've got the your usual UHF VHF capabilities with any sort of CubeSat that we've put up so far, 2 up and 70 down. But you can also get an X-band converter that's a 10 gigahertz model. They're available on eBay. I think Kent said that the latest models are $5. It's absolutely nothing. You're going to put that into your SDR. It's going to come out on some frequency, and off you go. They're very cheap because they're very popular in the EU, and you can't use the ones for Dish. You can't use the ones for the U.S. because it's not the right band. It's not the right frequency range. But they're very, very easy to get, very, very cheap to get. When we launched Golf 1, what are you going to need? Well, you're going to need the downlink, the down converter for the downlink, and then you're also going to need a transmitter that can transmit on one of the uplink frequencies. You can either use a rig that can do 23 centimeter natively, or the 1.2 gig, transverters, and typically you're going to need a power amplifier of some sort. This is where the 2.4 uplink to QO100 is kind of in the right spot, because you've got a lot of, let's say, eBay amplifiers that you can buy for real cheap that are supposed to amplify your Wi-Fi, even though you're not supposed to do that as a non-licensed user of the Wi-Fi. But it's great for us because now we can buy this cheap stuff that works on 2.4. You build yourself a helical antenna. Well, okay, Kent. All right. Well, Kent's going to give you his presentation later and tell you why I'm wrong. But PA1EW has had a success with a nice dish and a helix right here. So, and a GPS frequency reference for your uplink, because even though on the downlink, and I forgot to mention this, let me go back to this picture. If you notice, there's something highlighted in green right here. Ray Roberge, who is responsible for a lot of what the SDR does, the programs that run on it, which are all GNU Radio, he's provided a CW tone for the station, the downlink, so you can lock to it. If you think about it, Doppler gets worse as you go up in frequency. At 10 gigahertz, that signal is just moving. So you want something that aids you in tracking the downlink. That's why he put the CW tone there. So your software locks to the CW tone, corrects the frequency, and then can demodulate everything else. All right, so getting close to the end here, but how do I help? If you have terrestrial or EME microwave experience, and I know we have some people in this room who have done that, get involved. Talk with satellite operators about, Doppler, fading, all the problems that they encounter with satellites that go all the way up to, let's say, 1.2, or even those who have worked at AO40 on the higher bands, and create how-to documents, websites. For instance, equipment. What is WR90? Well, it's a waveguide. Well, nobody knows what that is, but maybe you can help explain it to them. Test procedures. How do I know it's working? Well, usually you can put your rig on a tripod and aim it toward a beacon. So continue to provide beacons and ground testing events. The pictures here, actually, the left one was an event out at NTMS, the North Texas Microwave Society that occurred last weekend. Out at Bob Strickland's ranch. Actually, Bob is in the audience somewhere if he raises his hand. There he is right there. Graciously let us all go out there and test our microwave stuff. Not me, I have no microwave. But a lot of great rigs out there, a lot of great setups, and I always learn a lot every time I go. Al Ward and John Schroeder, is that right? Yeah, Schroeder, doing some alignment on a dish out there. So these are the types of clubs that you want to get involved with so that you can gain that microwave experience you're going to need for the next generation Golf satellites. Future directions. Consumer devices are driving the use of microwave bands, which is great for us, good and great really. Cheap, highly integrated surface mount technology devices. But spectrum is money. So commercial interests will continue to ask for more, including our allocations. And the prime example is 3.3 to 3.5 gigahertz. We must utilize it and show that it's being used, or it will be taken away from us. And finally, AMSAT is committed to microwave on future satellites. We'll keep looking up in the spectrum, even to millimeter wave. With that, thank you, and I'll take questions.
Okay, my question is the antenna you showed with GNSS on it just covers L1 and L2. When L5 is a civil signal, also at 1176, you all should be considering that very strongly.
Okay.
That's my suggestion.
Okay, yeah, and that's something that maybe Jerry needs to hear as well. If Kent, I think Kent actually left the room. Oh, there he is. Kent, what do you say to L5?
Hold on, let me get him a mic.
Oh.
And then I'll bring it back to you.
The antenna is continuous coverage from 1 gig to 26 gig.
So it sounds like 1 gig to 26 gig continuous coverage. That ought to take care of L5 for you.
Okay, well that's good because and Jerry's asking me on the side, why L5? So about 15 years ago, the GPS community decided to incorporate L2 was primarily a military signal.
Correct.
And the idea was to have a civil signal, which is what L5 is, and it has safety life considerations too. But the most important thing is that it is a pure civil signal. It's wider and can provide more accuracy. So there's a lot of reasons why it isn't totally in use yet, but by the time you get your satellites up, it will be, and I think you need to consider that now. And a lot of the GNSS receivers have that embedded in it. So it comes for free. Just need to make sure you have it accommodated, because if you don't do it now, it's going to be a long time before you have it. It's all in the GNSS receivers that you can get. I mean, let me just say, the real inexpensive GNSS receivers that are flying in CubeSats have that in there.
Mm-hmm.
And not only just GPS, but also Galileo.
Okay, well, thank you very much. Any other questions? Oh, I think Kip here in the front.
Okay, now, from what I understand, this is a directional antenna, and it'll be pointing in the -z direction. And
Okay.
how much time in an orbit will we actually be able to see this, and how many times will it be seeable in the United States?
That is a good question that I do not have an answer to, but Jerry and or Kent may be able. Actually, Jerry, look at Jerry's. He's just begging to answer this question. So, actually, since you guys are coming up right after me as part of this, why don't you just come up to the front here, Jerry? And then Kent can speak from the back, please.
Whenever the bird is above the horizon.
Kent with his ever helpful commentary. You can't see it when it's behind the earth. Do you have an answer to that? What do we do? Okay, so I think, yeah, repeating the question is, what's the window? What do we think the window on a typical pass would be for microwave operations? Is it? And go ahead and get that microphone to him, please. Yeah, just the availability. Maybe I'm sorry. Which gentleman asked the question? Oh, Kent, Kip. Kip, would you restate your question one more time? Give him that microphone, please. So we need two microphones.
Okay. From what I understand, this is more of a directional antenna. It'll be on the Z- side of the thing, and we're trying to be pointing at the sun all the time. So that means Z is not necessarily pointing towards the Earth. Mm-hmm. So the question was, how often will it be in a position where we can see it somewhere in the United States where we are?
Okay.
All right, we're going to let our VPE answer that question.
In general, with Golf T starting up, that's purely to explore the technology, and the SDR is part of that. The X-band downlink antenna at the -Z has to be balanced with the sun we need for the solar panels, which we're not really sure what the trade will be to find. It's too close. Sorry about that. What the trade will be between finding how much sun we need, how much power we need, solar power, versus the angle of the antenna for the 10 gigahertz down. However, the 10 gigahertz down is pretty broad beam width, I understand. So it should be not necessarily having to point directly at you, depending on your ground station. If you've got a, really narrow beam width there, then that'll have to work with it. So of your 10-minute, typically we're going to be at like 500, like maybe 12, 15 at most minute pass. It's going to go pretty quick, and we intend to use it as much as we can. It'll be data downlink. That's what we have to prove. After that, then we will be looking at adding the voice via repeating the UHF downlink from the transponder.
There's another angle to your question which relates to what I'll call pointing control. And one of the modes that we are confirming that our ADCS supports is what I'll call pointing, say, to Earth, and then best effort rotation of the panels toward the sun. So one of the possible modes is you keep the Z pointed to Earth at all times, and then do the best you can to get the maximum power out of the solar panels, depending upon the orbit. So there's those kinds of plays that we're messing with from a control standpoint.
One thing to add. We don't know what the orbit will be. We know what we asked for, but we, being hitchhikers, when it comes along, it may be sun sync, it may not, and that makes a big difference actually. So we'll have to see what that is to make a final determination.
Okay, we've got Kent's got a question or a statement from the back there.
This is not the X-band transmit antenna. That'll be in my talk tomorrow. but the X-band is a patch array. It's aimed back at the Earth. Its pattern is roughly so that the width of the beam is equal to the width of the Earth.
All right, thank you very much, Kent. Other questions before I wrap up this section? Okay, I think we will right now. So this is actually part of the AMSAT engineering update. I went first, so again, I'm Zach Metzinger and 0ZGO. Jerry Buxton is up next, VP of Engineering. And Jerry, I'll get your slides set up for you in just a second. So warm round of applause for Jerry.
Good afternoon, everyone. And I'm going to have to go really fast since Zach took up so much time. I'm going to give a presentation about engineering and an overall view of everything and some depth on certain projects. Also, when I've gone through the slides, and Jonathan will be part of that, we have several of our engineering team here today. And I've asked them to come up and give a little 5-minute elevator speech, if you will, about what their system is or what they're working on. With could be anything from Golf to Fox Plus to an Ascent. Which buttons go ahead? This. I'm not really good with this fancy stuff here. I'm going to skip that because that was actually a leftover from the board of directors. But it's pretty much actually what is in here. A little bit about the team, and then the programs mostly, and a little touch on the future projects. So looking at the team, and this is an interesting statistic. We have about 35, 40 members perhaps of the team, and we had asked them to all give us their date that they started with AMSAT engineering. So I ran that through and put it into a chart here just for curiosity, and it comes up with a kind of an interesting look at who we have with us now. We have a couple different groups, the group of the first three there, and Bill Reed is the farthest left there. What year did you start in here, Bill? 1981? Well, I didn't say you're old, you just been. Okay, so in 1981, and then you see another one around 84, and then we jump up to the next group there. This group is actually what I would call the Fox group. These are people that joined in, including myself, although I'm not on there, during the Fox program. So we have several of those engineers that are still around. There were many more involved, but they have moved on to something else when they were done. They're fun. And the final group is the largest influx of a lot of new volunteers that I've seen in a long time. A lot of that credit goes to Frank and Jonathan for being in positions to reach out and look for volunteers. So we have quite a few younger, as far as having been with AMSAT, younger engineers, but all of them in whatever the age is, we have a lot of people, a lot of engineers that volunteer that are very smart at what they do. They're very dedicated into this segment of the amateur radio hobby in building various systems and stuff that go to space. In a look at what the value is that they provide to us, I thought, well, I'll do a little math based on a 40-hour work week, a nominal 40-hour work week. Most of our engineers, when we first sign them up, we ask if they can do 4 to 5 hours a week. And so you've got your family life, you've got all sorts of things, your day job, et cetera, that get in the way of the fun. And so running with a 5 hours per week for every engineer, I took 35 as the round number for the engineering team. So if we look at it against, say, if we were in the industry, as Robert mentioned at the meeting earlier today, so we've got 30 members working, and that would be 5 hours a week, and that would be give you about, or excuse me, 35, I should have updated that, about 180 hours. 150 hours, I can't read. Sorry about that. So 150 hours, and I round up to 160 to say, okay, that's easily divisible by 40. So we have essentially about 4 full-time employees working on all of the AMSAT engineering projects, and there are quite a few. I throw in a couple more full-time workers because there are some of us that I don't count myself, but there are some of our engineers who are invested into it and retired, and they spend a lot more time at it. So compared to a corporation, that's a really small number of people to be working on a satellite project, much less to be working, I mean just a single satellite, much less to be working all the projects that we have, because we have a ton of projects. And the big look at it in the corporate view is, if you take that 240 hours a week and you take an average salary of about $74,000 that I picked up off the internet, you come out with about $450,000 worth of labor. However, I think that our engineers are probably worth a lot more than that low starting rate. So, you know, we're contributing $500,000 to even $1 million perhaps of value to AMSAT through the work. Sorry. When looking at what goes on with these projects, I know that we say, hey, we're going to do a satellite. We're going to do Golf T. That was in 2017. Here we are 6 years later, and probably a few people wondering, why is this taking so long? What's going on? Well, I admit a lot of it is unseen. It is, one of the hindrances to making it public is that we all work from our own home. So we're all working alone. And to get even a picture of what you're doing, a photo, is you know, you got to con somebody into taking it or be really good with selfies and such like that. So there's not news that comes out that way. But the satellite that we're working with the golf and the golf program, it really raises the bar in what we're looking at for going to higher orbits. We have to have a lot more robust systems and thermal power and radiation protection if we're going to go above LEO. So in addition to that, we've got a roughly 1 foot tall, 4-inch square cube that we're putting all of these systems into. And we're adding more larger systems to what we do compared to the Foxes. We have, for example, the ADCS. Attitude Determination Control System is going to be key to our ability to maneuver, point the antennas, as we were talking about, or point solar panels for power and such. And the catch with that is that with all of our AMSAT satellites, you could build that satellite if you didn't want to put a whole bunch of radios in it. And that's what we do. So the space becomes a trade when you look at it, especially if we're going to add propulsion or something like that. We've got a bigger EPS, or electric power supply and such, and that squeezes down on what we can do with the radios. So even though it's 3 times the size of Fox, it becomes a trade on what we can put into it. One of the other instances for consideration is that failure is not an option. So we've learned that with the Fox satellites. There are a few of them that are not working nominally, but once they basically leave my home and I take them for integration, then there's nothing we could do to fix them. We did a lot of work through commands and software, changing some parameters on AL109, for example, and we're able to coax some more behavior, or good behavior out of that, productivity. But really, it's very limited. Even knowing why something doesn't work is an educated guess, but still just a guess. We also have, as the #1 risk that is listed in the CSLI, the CubeSat Launch Initiative proposal that we submit in order to get the Alana launch grant from NASA, the highest risk is that we have no redundancy, basically. And so our volunteers, the people that are interested to volunteer, may be a single person working 1 or more systems. And the loss of any single person, whatever the reason is, the loss of that input 4 or 5 hours a week or 45 hours a week is just a major hit on what we do, and that slows productivity as well. We've also been dealing a lot, especially since the COVID era, with supply chain issues, just like everybody else. And we were looking at extremely long lead times on components that are basically kind of run-of-the-mill, although we look for automotive-grade stuff in a lot of cases. But I recall at one point in time, it was 54 weeks lead time on some of the components. And so that causes a scramble to look for stuff, alternate sources, or a delay to order and wait till something happens with that. And in doing that, we will often buy lots of that component in order to have them for a couple, 2 or 3 or 4 models of the Golf T for people to be working on. Engineering model, flight spare, and the same thing with Golf 1. So maybe call it 10 different satellite uses. So we order those in lots in order to protect against future difficulty in acquiring them. There's also the fact that a lot of things go unobtainium, or the end of life, that leaves us either having to redesign or having to abandon. The Fox 1s, really, one of the biggest reasons that they were not continued is because there were so many parts in it that were no longer available. We'd have to redesign half of the satellite, and that was not worth the effort for that. Whereas we are moving into Golf 1, or Golf T and Golf 1, which can do the same thing with the newer construction. So let's see what else. Oh yeah, there's always also, you ever go to the store and get any potato chips and Coke lately? Costs about $100, right? And so does everything else that puts in the satellite there. So the costs are going way up, and that does take some planning to make sure, and that goes back to, a little bit to the buying quantity. We're not at PDR yet, preliminary design review. So when we're looking at those things, we're looking at them with the idea that we're pretty sure we're going to use it. So we go ahead and buy a bunch. Or if we're not pretty sure, then maybe we wait a little bit and evaluate it some more and do a little more prototyping or something. And we do have, though, and have had lately, some very good donations that have built up the bank account, if you will, AMSAT. And so that gives actually a lot of relief to our ability to overcome buying in lots, buying a bunch of stuff, and also buying newer equipment like the attitude control system, which is a leap. I think I could probably say that that full system, engineering model, flight model, just for Golf T, will cost more than the Foxes, all of the Foxes put together. There we go. So we have, under the engineering umbrella, 3 programs that are running. I'm sorry about that popping. Can you hear me okay here? Okay. I have a tendency to just want to be right in front of that podium, hides my belly, you know. So we have Golf. Golf is the, and Zach talked about that a little bit, greater orbit, larger footprint. Golf, we have Ascent and Fox Plus. Fox Plus is fairly new, that was introduced to us by our newest, well, relatively new Assistant Vice President of Engineering. The Golf program, greater orbit, larger footprint, the idea of it is, in 2017, I put it to the board of directors. We had opportunities in the form of attitude determination control system partnership with Ragnarok, whom we previously worked with on the, what you might have heard is the CQC, the CubeQuest Challenge, a lunar orbiting satellite, Derby, that NASA had sponsored. And the goal of that was to see who could return the most data from the moon, or even beyond. You could go just beyond the moon out into forever. The Ragnarok, the corporation, Luigi Ballerini pulled together a team of various systems operators, if you will, to build this satellite. And it came to us that the communications and ranging was something that was in need, and that we certainly are good at, is the communications and ranging. So that started the whole process with that. In the end, that satellite was not selected for the SLS launch, which meant that they could still go, but it would cost something like $1 million. And so that was the end of that project. In that, Ragnarok, still wanting to continue development of their piece of it, the attitude determination control system, came to me, and we partnered on the idea that we would be able to give them some flight heritage and get at a low cost attitude control system for our new Golf satellites. Golf had been discussed for years before it was introduced. As we put together the Fox satellites, there were a lot of opportunities that we would be together, maybe at Symposium, maybe, I remember most at a taco shop as we were doing environmental testing on one of the Foxes. And we would sit around and hash out ideas. It's your napkin exercise, I guess you'd say. And the idea of Golf is that we will develop our systems, build if we can, and acquire if we need to, systems that are going to be needed when you go to HEO. Golf is not intended to go to HEO. Golf is intended to teach us how, so that we have the expertise and the availability and the capability to do attitude changes, to do propulsion, to either work on our orbits, raise them, lower them, and also for collision avoidance. They have to have maneuverability. That's part of the orbital debris rules. So there are a lot of parts that go into that, and they require precision in what you're doing. Because if you're going to make a satellite move, you have to be very sure of your pointing and very sure of how much gas you give it, if you will. So that's something that we really need to study before we put something, up there and go, okay, let's push the button and it'll go to HEO or something. Also, along with that, the need to develop more power, systems that get more power, and that's the solar wing development. And overall, the plan is for several Golfs to be built, and this was before ODAR was clamped down. So the idea was we would be able to step up, start with a LEO, go to a higher LEO. Golf 1 was originally intended for 1,200 kilometers to be up there around FO29 and AO7, and then maybe some MEO, and getting that harsher environment, getting the capability to maneuver and steer and point the spacecraft, and the essentials we needed to not only have, but to know how to work all of these systems. So that got nixed, though, for the time being, by the orbital debris. We still plan on progressing with that. Golf T, going to Leo, we really need to just do that because anything that follows needs to be from what we find out with Golf T. Golf 1, I'm still looking for opportunities to higher orbits, and then we'll go beyond that. This is kind of just this is the view that we submitted to NASA for the orbital debris for the original launch that we were going to have with Golf T. And so it represents the Ragnarok ADCS, but the systems inside and the solar panel array that's put together and such gives you an idea of everything that goes on in there. I hope you can see it okay. What we basically have, got a laser, is this is the stack that we used. Sorry, I can't see it that well. Yeah, this is the 8mm spacing stack that we used in the Foxes. That contains a lot of the components, the systems that we're flying, that are similar to or the same as in some cases. And you go up in between it, you've got some switching with the RF matrix that Zach talked about. You've got the CIU, the central interface unit, or common interface, I forget. That's the junction of all of the signals in the satellite to the sections of the satellite, which would be the attitude control and EPS, or our typical Fox avionics, if you will. And the solar panels, that's the input from the solar panels go to the CIU to be fed through that. Yeah, that's good for that. Any questions on that? Sir.
Jerry, I did have one question from YouTube. It was going back to purchasing components. You had mentioned that you were purchasing components in a bunch. Could you quantify that any more, particularly for our questioner? Thanks.
I was going to say big lots, but I don't know how many people are from Texas or how far out there. Well, as an example, in Fox, we would place orders because I was the one with the money, the credit card. I would have the engineers that would make a cart of the components that they needed. And then I would go pay for that off of DigiKey or whoever. In some cases, even just between the time that they did it and the time that I got there, they had a part substitution already, or missing parts, and then I'd flip over to Mauser to get that. And in some cases, you had to buy 10 of them at that time. So this is, many years ago. Wow. 7 or 8 years ago anyway. So, I wind up buying lots of 10. Since then, those multiples have grown to bigger lots. In other words, you got 10, 25, maybe 50, 100. And in some cases, we've had purchases of 100 units of whatever that particular component might be. That's what I mean when I say that we bought them in bunches. So sorry for not being clear.
Nope. Thank you, Jerry, for clarifying that.
All right. I did mention, actually got ahead of myself a little bit on the slide. This is about the idea of the golf program and what we plan to do. The perk, I guess, for this stepped method of learning and raising our orbit was that we're building a little bit different mission each time. Maybe one's got ADCS, one's got propulsion, depending, or a new type, checks and batteries, different solar panel array, stuff like that. Everything we want to tweak and understand the best we can as we go higher into orbit. But when it's done with the experimenting, for example, Golf T, then it's another ham satellite. And that would be the same as we go. Therefore, there would be these still populating satellites to hopefully progressively higher orbits that are available to the satellite users everywhere. There's 2 projects then under the Golf program. Golf T, which I mentioned, and Zach touched on that a bit. These were both funded in 2017 when we had the opportunity for the ADCS, which kind of gave it a little push compared to what we were planning of when we would start it. But with that available, I went to the board to seek funding for Golf T, and then actually went back for Golf 1 after some discussions. And when I learned about opportunities for some possibly higher orbits. So we took that there, that was the kickoff of the golf program. And again, it was something that we had talked about, that is, we being some engineers and myself, so that we all had a plan of what we were going to do. The ADCS just gave it that impetus to go, let's just do it now, because we can get this now, we can test that now, and it was going to be the next step anyway. Both were approved. I submitted the CSLIs in November, and they were selected. Now, so selected, in other words, they agreed that your proposal was sound and that it met their goals for what they're looking for in spending their grants that they have. It's essentially a grant. They pay for up to $300,000 of launch costs, which covers pretty much everything up to a 3U to LEO. So that's the free launch part of it, if you will. And that means that when you're selected, doesn't mean you're guaranteed. It means they'll look and they will find something for you. Typically, they have always come up with something. So it's a good ride. Like I said, it's hitchhiking. You're going with whoever it is, with whatever their delays are and changes in orbit, et cetera, but you get a satellite up there for a budget price. The T is the technology exploration environment, and I pointed out some of the specific systems we want to look at with that. That's the solar panel, deployable solar panels, and this is an in-house design. They are not steerable. They simply flop open, if you will. And that raises greatly. Let's see, you would have 28 cells if you just had the static cells around the four sides of the satellite. The top and the bottom, because of the antenna, and in this case, I think we're going to go with the magnetometer, but those are taken up. So you would have 28 cells. If you add the wings, you've got 42 cells. So it's a significant increase in the amount of power that we can have available. I got a bigger picture of, geez, it looks so small on my laptop when I was doing it, right? I was going to say I got a bigger picture of some of these, but I'll talk about those shortly. So in the solar panel, deployable solar panel department, we also obviously needed a new space frame for 3U. And it came to pass that we filed a request for a grant, I guess you'd say, with the ARDC to fund this. And they did accept that. So the ARDC is underwriting the creation of the 3U space frame and the deployable solar panels that work with it, if you will. The 3U space frame should be good on its own. And that has been because ARDC's, preferences, and ours actually, it's open source. So it's being worked on as an ascent project where we can do it, removed from a particular mission at that particular time, although that's the closest when we get to a particular mission. But it's all done open source, and open source then is something, like I said, we've been looking for a long time. We have the opportunities now to start doing that, and this was kind of the catalyst for that. Beyond the solar panel that is being developed specifically for Golf T, the idea is that could, if it's successful, also be expanded to project to have more deployable sides to it, if you will, or maybe another row of panel or cells on the end of each panel to increase the power opportunities. In the Ascent program, which I've mentioned and Zach might have touched on, one of the things that came out of the program was the radiation tolerant IHU. That's something you were involved with, Zach, that is. The idea of it, we had a lot of experience watching the STM 32L151, I think, processor flying in the Fox, and we had predictions about what radiation might do to it through upsets and such. The design of Fox was simply that if it got an upset and it rebooted, then pick up where you left off. So there were no really critical systems tied to it. And we did find that we would have resets primarily over the South Atlantic anomaly, although they can occur anywhere. The radiation tolerant IHU uses two separate chips and two separate processors, and they work together. One is the primary and the other one's the standby, basically. If an event happens to one or the other, or for whatever reason it locks up, then the other one takes over right away. And therefore, we're looking at the idea that if you have a single event upset, for example, caused by a proton, it's going to hit one of those, but not both of them. And that is the expected increase in the tolerance for higher radiation, at least at LEO, and maybe up to 1200 where we're going to fly Gulf 1. And beyond that, we'll experiment some more. The IHU that was on the Fox 1 satellites, which we'll refer to now as the LIHU, as in legacy, will also be flying on Gulf T. That provides, first, some redundancy, and second, it will be a comparison with the RTIHU for the relative number of times that has a reset versus the RTIHU has a reset or failure. In addition, there's an experiment from Vanderbilt University, Vanderbilt ISD, a radiation experiment, as we have flown on many Foxes, where they're looking at the count of low energy proton hits and what the results are in various commercial off-the-shelf parts, such as memory and processors and such. The experiment that they fly will be similar to the ones on the Fox, and that adds a third look at the RTIHU's capability to deal with the radiation, because through that we can get an idea if the environment is, when something happens with either one, if the environment is either the same or worse or some big difference between what we had seen with the Foxes. So it adds a little, it's not in any way scientific, I should say, but it is a comparison for looking at RTIHU performance. The RTIHU also has a radio with it. It'll do VHF and UHF or crossband, and that is going to be used for the commanding and the telemetry, the direct access to RTIHU, because we plan that would be by itself on Gulf 1 with success. Just little blown up pictures of it. It's a little fuzzy, but did you show anything about this? I did not. Okay. Well, these are the two processors, right? Anything else you want to say? Yeah.
Hi, everybody. Zach again. So the RTIHU has two processors, as Jerry mentioned. Each of them is a TMS 570. They call it the Hercules. It's an automotive-grade safety processor, which has two Cortex R4F cores in it. And all it is it's a 32-bit ARM processor. The two cores are in what we call lockstep, so that there's something inside, some logic inside, that's running the same code on two processors and watching the difference between the outputs on these two processors. And if it differs between the two, it says, oh, hey, something went wrong, and signals a fault. It has what they call spatial diversity, meaning the two cores are separate on the die. One of those CPU cores is actually rotated by 90 degrees, so it's got even some additional diversity in space. And they're running one clock cycle out of phase with each other. And these things zip along. I've actually forgotten how fast they are. Burns, do you recall the speed? Yeah, it's up there. It's in close to 100 megahertz, I believe, or over. And you might think one clock cycle at 100 megahertz is pretty fast. When you're talking about a heavy Z particle hitting you, that's an eternity. So by the time the particle has gone through your silicon, you haven't even finished that last cycle that you were on. So if you do have a bit flip in logic, you get that immediate indication that there was a fault, and that signals a fault, dedicated fault hardware inside the chip. In the center of the device here, in the center of the RTIHU, is the arbitration logic. And it's real simple. It's just a couple of 7400 series devices, logic devices, that watch the outputs of the faults from each of these two chips. And at power up, it's sort of a race condition. Whoever clears their fault signal first gets the bus. And so these are the bus switches down here. And then that chip maintains control of the bus until it has a fault. As soon as that happens, this arbitration logic shuts off these muxes, turns these muxes on, and then indicates to this processor, you now have the bus. Through the magic of Burns's software, Burns Fisher over there, and a private CAN bus between these two devices, there's a state vector that's always being updated. So if this guy is in control, for instance, this one over here has all the data it needs to know what mode the satellite is in. So ideally, when this second processor comes online, the first one has failed, the user will never know that the RTIHU has failed. Burns is kind of shaking his head, but I know you've done it a little bit. There's a little bit of time, but yeah, he'll get his chance to talk about this. The idea is to maintain the maximum amount of uptime without having to reboot the satellite, put the satellite in a situation where it doesn't have an IHU anymore. On Gulf T, there will be not just the RTIHU with its two processors, but also the LIHU, and they're all connected via CAN bus. So they all kind of know the state of each other. So we really have 3 redundant ways of controlling Gulf T. As Jerry mentioned, on Gulf 1, we hope to eliminate the LIHU just because, you know, it's tough to carry around extra mass, extra power. The STM, I think it was the STM32 was, the original one. It has definitely served its purpose, and it was a great design. A lot of the things that are on this board, there's a lot of power regulation for one side that was taken from the LIHU design. The other side has some experimental switchers on it, and we'll see which one lasts. So if the switchers on this side die, and we have to just rely on the side that's got the linears, well, we've learned something. That's good. Jerry also mentioned that we have a AX5043 radio modem, and this takes an SPI bus. It's meant for sub 1 gigahertz devices like, the Amazon buttons, if you guys ever saw those, where you hit a button and you get something ordered. If they weren't the 2.4 gig Wi-Fi, they were the sub 1 gig chips like this, which contain a modem and an RF section and an amplifier. But then it also has an external power amplifier made by NXP. They can give us, nominally about a watt, but we're seeing about 3/4, depending on the matching, as the downlink for that UHF. It has a separate uplink path that we can use to receive commands. And because these two processors are connected and they know each other's state, the RTIHU software has a neat mode where one of these radio modem chips is listening continuously to 2 meter for commands, and the other side is being used to transmit telemetry continuously. These chips are not full duplex, so you can't listen and transmit at the same time, but by creatively using the two sides of the RTIHU, you can emulate a full duplex system. Now, to be clear, this is just for command and telemetry. This is not for user traffic. It's not a PACSAT. It's nothing else. It's just for AMSAT operations use. But I believe Chris Thompson actually has had his software demodulate. And I'm kind of looking at him. You got it to demodulate the RTIHU's telemetry, correct? Yeah. Okay. So it works just like the Foxes right now. Pretty much everything I had. Thank you.
Thank you much. I'm going to do that again with the next system we get to here. The ADCS. This is the Attitude Determination and Control System. Ooh, sorry. And originally we were going to go with Ragnarok as the provider of that. Ragnarok was unable to meet the timeline necessary for the Gulf T launch. We had a launch actually manifest at that time. So we had to back out of the launch opportunity and look for something else. So what we found was one of our members, Hilly Page, who is, I don't recall his call sign, but he is out at the University of Arizona, is that right? out at the University of Arizona, and he's a graduate student there, and he has, he's graduated, and he was working on an ADCS for another CubeSat mission that they had going out there. He was able to give us a really thorough rundown of the various ADCS that were available commercially and their value bang for buck, if you will. He also had experience with this particular brand, which is the CubeSpace ADCS. So that led us to where we have purchased, or we will purchase and use the CubeSpace ADCS for our systems. Right now, in the development of it, we have their flight computer, basically they call it the Cube computer, just to work as an interface to make sure that we can interface with their flight computer from our IHU in order to receive and send commands and various information of that sort. It does provide 3-axis control. It does have an option for star trackers. We don't plan to use them right now, and it will be able to use of magnet torquers as well as reaction wheels for our purposes. So that's a device under test with this as well. Have they flown before? Anybody remember? I think I'm pretty sure they have, or at least they've sold a lot of them. So, but it will be for us that learning curve. Not only do we, engineering, have to figure out how to talk to the ADCS and understand what it's saying and make that into a meaningful communication, but we have to design the capability for our operations, which is Drew Glassbrenner and Mark Hammond, to be able to send commands to the satellite and point it in a particular attitude, and then also receive the data that verifies that or gives them an idea of what they might need to do to point it. So it's not just a engineering problem, if you will, to get the ADCS integrated, but we also have to be able to provide a user-friendly interface to ops to be able to operate it. Got some blowed up pictures of this too. The one on the left is actually a 3D printed representation, a model of this portion of the satellite. And Tom Karnauskas did this. He's working on getting the stack inside of the frame. And that was his challenge with this one. You'll see we do have offset rods because of the size of the ADCS versus the size of the rods and the circuit boards we had on our typical bus. Here's your EPS right there. And then you've got MPPT and the CIU sandwiched in there. And, whoops, sorry. Well, I hope you enjoyed that. Let me see. Come on. There we go. And the computer board for Cube computer for the module. And then over on the right is their flyer image of an entire unit with all the whistles and bells. And so ours will be similar to that. We have the SDR and 10 gigahertz data downlink. The 10 gigahertz data downlink is working for high-speed data downlink. This is something that has come up through some of the industry shows we go to, where prospective parties, interested parties in partnering, typically universities, we will, of course, fly experiments for them. We carry that for STEM experiments. And it turns out that our data speed in the Fox satellites that was perfectly satisfactory for Vanderbilt, as well as the Virginia Tech imager camera and the University of Iowa Herky experiment, which unfortunately didn't work to its fullest extent, so you haven't heard much about it. But they were talking about high speed. Therefore, in looking at our move to microwave and the ability to provide some data at a higher speed downlink, that's what this experiment's about. It uses an Edis E10 SDR, and its primary mission is solely to bring that probably our telemetry, unless we preload some other stuff in it to keep it busy. but to do that downlink there for the test, at least to satisfy the CSLI. Beyond that, because it became something that was early on rather easy to achieve, kind of like the L-band downshifter that Zach talked about, where we could put a board in that Fox satellite and have an L-band uplink without really changing much. The ability to have the 10 gigahertz through the SDR repeat the downlink that's coming from the transponder, the VHF up, UHF down. So the SDR just picks that off, and then it will also transmit it down on 10 gigahertz, which is something that we're going to find useful for. My idea, my plan is that as we transition to more microwave things on the satellites, as we go higher, which is where they really become important, having something like this now gives people an opportunity to experiment. And the voice part of it gives you the opportunity to operate the transponder like you would basically on the uplink, but listen for it on the downlink on 10 gigahertz. A closer view of some of the items Zach had shown earlier. This is the PA, and that's the radio. Now see the way the radio sits, I'm sorry. It is a size that isn't anywhere near what we would like to fit into the stack of the satellite, but we cannot alter that. We had asked them actually if we could take the PCB and kind of rework it so it would be a little bit smaller, but they did not allow that. So the way it works out is that this particular satellite's got this really goofy stack arrangement where we have, like I said, this is some of the legacy stuff in a sense right there. And this is the new stuff, which includes the SDR power, et cetera, or ADCS and power and such. And then the SDR is just kind of stuck up against the wall here. And that was a little bit of a, well, that's one of the things that makes things go slower, right? When you're working on that and you've got to go, okay, how are we going to fit this in that 12-inch cube there? But that worked out. Hopefully we will be beyond that. And you can hear a little bit more about that shortly, but there's a project in Ascent that we call SDRB, where the work is being done to redesign the basic function of the E10 down into a 4-inch square, roughly PCB, which is what we use on our stack. Golf 1 then. Golf 1 is not a lot to say about it right now. It's going to be dependent upon, but hopefully the same mechanical design as Golf T. It will also carry the same ADCS, assuming we have no problem with that, and planning on expanding perhaps the power, the battery cells from a 4P2S, wasn't that it? 4S2P. Well, add another bank of batteries for more power. Does it do it again? 4S2P. Okay, 4 serial 2 parallel, and make it a 4 serial 3 parallel in order to give us a little extra boost. Because with Golf T, we know we're right up against the power margin for everything that we have in there that we want to run. So that's going to be another thing that we'll learn from it, is the balancing of that in order to get the best performance. Adding a little bit more capacity will be good. That becomes a volume and mass issue though too. The final design then of Golf 1 is based on Golf T. We are learning things as we design Golf T and go into preliminary prototyping and flat sat and eventually engineering model, for example, of what works or doesn't work. So we have that knowledge already going into Golf 1. We will learn more, especially when we're done with the flight model of Golf T, and hopefully get some experience with Golf T on orbit before we have to close Golf 1. So the schedules for those right now are that Golf T, we plan, the target is to deliver it in the second quarter of 2025. And typically that means that they've got the launches down to where it's about 45 days from delivery to launch. So that'll put launch somewhere around the middle of 2025. And then ask take about 18 months from our completion of Golf T, and this depends on how many people we have and such that we might work ahead, but before we launch Golf 1, before it's ready, December I think I made it November. November of, could have been October too, fourth quarter of 2026. And so that gives hopefully enough lag that we do get a little, like I said, on orbit telemetry and observations and lessons from Golf T that we can work into it. We did not have that opportunity with the Fox satellites. They were so popular, and we had Vanderbilt University even submit 2 of the CSLI for them, that those just wound up being kind of cranked out like toasters or something. And so what we found out wrong with Fox 1A, we made a little tweak. We were able to make some software tweaks with them, but nothing substantial like was envisioned originally. In Golf 1, we go back to our educational platform, if you will, where we have ham radios with some experimental stuff in that league, and then we carry STEM experiments. STEM experiments is one of the greatest outreaches I have seen to education, involving students in creating experiments for whatever the case may be. In this case, for Golf 1, we're looking at high school in San Diego has the desire and has been working on a camera experiment, so we can, or they can take images, if you will. And you can't beat that, in my opinion. You've got the students, they work on this experiment. It's something that needs to fly in space, and we're an easy ride in a sense, right? So they don't have to try to build a satellite around it, because that's a tough part of trying to do that. So also Vanderbilt, again, Vanderbilt ISD, as I said, are close partners and regulators. They're testing COTS things, testing radiation testing things that we're, you know, that we will use or fall under our projects and such. I'm sorry, what?
I said our stack was pretty full. Where are these going to fit?
Oh, those? Yeah. Well, if we, for one thing, it's shrinking down the what do you call it, SDR. You take it, and getting the stack back in the order of being a stack. The Vanderbilt experiment is two boards, and there is quite hopefully, a gap between the 2 stacks that are there. And the camera is very small. It can probably be mounted to the wall, in a sense, like the SDR is, with no problem. That's the current view. It can look out the -Z, the end with the 10 gig microwave antenna on it, the patch antenna array, because it just needs a little hole between those, and that's a possibility as well.
Okay.
And yeah. Just in general then, saying that is that when we can get an SDR to be stackable, then we can go back kind of the old game of just putting everything in vertically, essentially. One moment, please. I don't know how many of you are from Texas or have ragweed allergies, but antihistamines dry you out really well. Thank you. Sorry about that. And then we've got, of course, the microwave. And Zach talked about this. We have, with what's on Golf T, the ability for the 10 gigahertz downlink. We have ability for, pardon me, well, I don't call it necessarily an uplink, but we do have that 432 or 70 centimeter, which kind of initially started as a pickoff in order to get that transponder signal to be able to repeat down on 10. We have in that multiband antenna 1.2, 2.4, 5 gigahertz. The long-range target for AMSAT was what we called 5 and dime. That had 2 very good starts with the CQC, the CubeQuest Challenge lunar orbiting satellite. That is actually where that originated, as the engineers there looked at the volume that was available and what frequencies would work best for the communication with that satellite, essentially. And it was based in part on the fact that both 10 gigahertz and 5 gigahertz have typically surplus or consumer components available for work on ground stations and such like that. And then over in Europe, as you know, they have QO100. QO100 uses 2.4 up and 10 gigahertz down. So we have the opportunity of, in Golf 1, operating 5 or 2.4 or maybe both as uplinks, so that if you're up, when they want to use it, it would be no change. Essentially, they wouldn't have to have a 5 gigahertz piece as well. Pardon me. And so that gives a lot of opportunities. The 1.2 gigahertz is not worldwide. And actually, I've had some fun with the ITU when we put up the L-band satellites, because countries would, you have an opportunity to call for a coordination, I guess, with particular countries, and they would send stuff to the FCC, and then that would come to me, and they're saying, well, your 10 gigahertz there is going to mess with our, 1.2 L-band is going to mess with our local GPS satellites or what have you. Fortunately, I was able to say only, tell your hams not to use it then, and it won't be a problem because it's not a downlink. So as an uplink, and especially over the U.S., I think it might make a good command channel. That where we're going then too, with the 10 gigahertz, is that you've got a lot more bandwidth to work with, right? So, like 20 megahertz transponder or something, for a dumb example, but an example, then you're going to want 20 megahertz worth of stuff to uplink, possibly, and therefore if you put it on 5, you got that. Even 2.4, I'm not sure how much you will fit, but the 1.2 then is a good way to get out of the way, because the VHF, UHF capability will continue, and it will be omnidirectional as it is now, at least for Gulf 1, because we need that fallback. I'd like to get a time check.
You do, Jerry. So, yeah, I think we're going to do a break here pretty soon. We've got about 9 more minutes, and we're going to do the Fox Plus after the break. So if you want to take some questions now, or I don't know when your transition is, if you would go toward that. And you're muted right now, by the way. Okay.
All right, I'll just go faster. Ascent is the Skunk Works. Skunk Works was proposed by Dr. Tom Clark back in 2015 as a place for engineers to go develop things that are just in a sandbox, go play. So that is what they do now, and that is what has created some of what is flying on Gulf T, Gulf 1. And we have much more activity there, which is something Jonathan had on his bit of slides here. It's turned out to be a really good thing, because it's free of being tied to any particular mission. So in the case of Gulf 1 or Gulf T, for example, Gulf 1, the design of that satellite incorporated some of the stuff that was thought of in Ascent. So that's how that's kind of intended to work. It's not targeting a particular thing necessarily. And this is where we cut it. All right. So questions?
Just kind of overview of power budget. When you have the deployable solar panels, when they're fully illuminated, how much total PV power total from all sources will you have? And number 2, how many watt hours of battery? You're talking about expanding the battery. How many watt hours of storage will you have there? I'm assuming the PV panels are going to be illuminated roughly 50% of the mission.
In looking at the design, the idea for those deployable fixed panels, it was calculated at basically 3 different levels. One would be full sun, one would be about 45 degree, and one would be less than that. And the total capacity at full sun was on the order of 19 watts. Is that right?
36 or 37 watts.
Okay, I'll go with that. Full on sun. 36 or 37 watts straight on. Yes, and the calculations were that if we're going to allow for the fact that we're going to be testing ACDCS or pointing the antennas toward ground, then the average would be something about 20 watts. And that's what we're working with right now. And that's only the number I recall. If anybody, other engineers here, have a better answer, I appreciate it.
Was that average over the orbit, or just when it was at a certain point? When you say the average.
Yeah, I know. I'm honestly trying to remember specifically. it's something that I don't think it was
Okay.
orbit average.
Okay.
I think it was average that we could generate.
And the other question is, how many watt hours of storage were you thinking about putting in there with the battery? And what technology of batteries?
Is it what they're lithium iron phosphate, right? Lipos and the bank that we have right now. I think the cells changed from when I first recall looking at it specifically, but we're talking about somewhere around 78 or 80 watt hours. Is that true? With the increase, the increase to third string, plus they were a little bit bigger cells. So, but originally the Golf T was specking out at 141 for that launch there. So that's what I hope to get back to, close to that. Anything else? And I apologize, I kind of got shorted on time a little bit there. I'd still like an opportunity maybe for all the engineers that are here to either answer questions or come up and do a little elevator speech. I think that's very valuable compared to what I do based on trying to remember everything they do.
Exactly. I think we have time for a few more questions, just maybe 2 more questions. I've got one in the back corner here for you, Jerry, and I've got one up front, so just a second.
So I wanted to know if you're transmitting 1 watt down, but just 1 watt transmission power down.
On the
We'll say on the ham bands.
Excuse me again. The last part?
On the amateur radio bands.
Yeah, I
transmitting
realize
1 watt down.
It depends on what radio is working. Is a short story.
Okay.
Golf T is flying the same transponder as AL 109, which is kind of like an average of 650 milliwatts, I think, right? And then the SDR. Honestly, I don't know the straight answer to that right offhand. How much is the SDR doing? We're doing about 2 watts, I think, or something.
So if you go higher altitude.
We'll boost that.
Okay.
See, the
Okay.
CQC, the lunar one, and also Phase 4B was going to use the same thing. The PA design was done for 10 gigahertz to provide 10 watts out of a module, 40 watts total in the case of Phase 4B, or 20 watts from the CQC by 2 antennas, 2 finals there.
I think you were the one that answered earlier a wide beam width is expected. What does wide mean? Is that like 15?
That's a nice broad one,
45?
Isn't it? Well, Kent stated that what it is in the X-band case is that it will cover the whole Earth. So that it's, and I don't remember what that number is, but essentially in talking about that radiation pattern as well, he said it can be more off the side. So the idea is that it doesn't have to be pointing directly below, and it gives everybody a better opportunity to be able to get it, especially since it's going to be scooting it, in Doppler at that height. I'm done. Thank you, everyone.
All right. Thank you very much, Jerry.
Can I do a quickie? I'd like to ask all my team that are here to stand up, please, for just a moment.
All the engineering? Yep. There we go.
Yeah, all the engineerings. And I'm gonna here comes the bus, guys. Okay, so what I'm thinking is, because we didn't get the chance for Q&A and such like I thought, would you guys be willing, if anybody wants to come up and ask you something about your system, in general, to just go ahead and talk about it? They're going to give you more detailed answers than I can, and so we'll work that out, but I think you'll be able to ask them for some more detailed questions.
Thank you very much, Jerry. A round of applause for Jerry, please. Jerry Buxton. We will be taking a break right now. We will have a slight change in the presentation order. We're going to do the Fox Plus with Jonathan Brandenburg after the break. So from 3 to 3:15, there is a break. Frank would like me to tell you there's water in the back over there on the left-hand side. And if everyone could be back by 3:15, we'll resume at that time. So thank you very much. Back on? Okay. Hello, everybody. If we could take our seats, it's coming up on time to get started again. Hey, everybody. Hey, everybody. How you doing? It's time to get started again. Hey, Burns. I'm talking to you, Burns. Hi, Burns. Hello, everybody. All right. Time to take your seats. We're going to get started again. We'll wait just a minute or two for everybody to take their seats, and we'll get started again. I'm sorry. I'm talking as if I talk any louder, I'll probably break something. I don't know. All right. So the folks in the back there, Kent, are you ready? Everybody? All right. All right. Let's get started again here. Thank you again for coming back promptly and after that break there. We are going to continue with the last half of the engineering update. We'll be hearing from Jonathan Brandenburg, and he's the Assistant VP of Engineering working on the Fox Plus program. We'll hear from him. And Jonathan, are you ready? All right. Please give him a warm welcome. Jonathan.
All right, welcome me. Everybody, are you ready for me? We have some sidebar conversations. Shall we finish those up and then we can continue? All right, because that's the kind of person I am. Good afternoon. I'm back at it again. I'm here to talk to a little bit about the Ascent programs and the Fox Plus program. And I have the exciting opportunity, being assistant to the Vice President of Engineering, as he likes to call me, to work on a variety of tasks as I volunteered to take on the Ascent program and volunteered to take on Fox Plus. So I'm going to be covering a lot of different projects at a fairly thin level, but I will be pausing frequently to answer as many questions as I can and deferring as many questions as I can't. We're in slideshow mode now.
Yeah, and I'll put it on here.
All right, thank you. That works. So Jerry already talked a lot about the deployable solar panels and the 3U structure as being part of Golf T and the golf program in general. So I'm not going to repeat most of what he said. But I do want to point out this is an Ascent project, and as he said, this is primarily an Ascent project because we're using this as an opportunity to really start pushing our open source techniques, our open source processes, so that we could share this as openly with the community and the world as we could. So that's why you'll find it here. We've had some really good progress on the 3U structure. Mr. Tom Karnauskas has put a great deal of effort into mechanical models of the 3U structure. One of the big achievements, and I do really consider it a big achievement, is that we as AMSAT have acquired and begun to standardize on some modeling software and providing the tools to our volunteers. So we're not necessarily always requiring our volunteers to bring their own tools to work. In certain circumstances, we're able to help with that, and that's the case with the Inventor modeling software. As part of that, you saw the picture, but now I hold the physical 3D printed model. Mr. Tom Karnauskas has printed a very nice 3D model of half of the Golf T satellite. This is the half that has the reaction wheels and the ADCS system, the batteries, the MPPT board, and an interface board there in the middle. So these are the half of the satellite that controls the power and the attitude. I'm going to go ahead and step out of frame to hand this around real quick, just so you can look at it if you want. You'll recognize reaction wheels. And I'm back. So Tom has been working very closely with Dwayne Moberg on the deployable solar panels. Now, having said Dwayne's name, I also want to recognize Vincent. Vincent was a volunteer, and he's re-engaging now that life is allowing him to do so. They're both making good progress on the deployable solar panels. The key here on the deployable solar panels is the primary challenge is how do you pack in 3 layers of solar cells on backplanes into the pockets on the outside of a CubeSat, and that's been a real challenge. So you have to get each cell and all of the little connectors, the little hooky thingies, that's a technical term, hooky thingies, that attach the cells to the PCBs as thin as possible. You still have to have cover glass to protect the cells. And then most importantly, and this has always been the real challenge here, is you need a hinging mechanism and a flexible cabling mechanism to go past the joints. And Dwayne has selected some preliminary hardware for hinges and has started working on the cabling to go around those hinges. So I'm actually very excited by the progress here. I hope the next time we talk, I'll be showing you physical engineering prototypes, maybe is what I'll call them, of both the 3U frame and the solar cells the next time we have this opportunity to meet. I said I'm going to pause frequently to answer questions. This is one of those times. Do we have any questions that I could possibly answer with that brief overview of the solar panels and the 3U structure? Okay, that's okay. That's okay. My feelings aren't hurt. All right, moving on. We do have a lot of ASCENT programs and ASCENT projects, I should say projects. And I want to remind, again, ASCENT projects are basically research and development projects. They're opportunities to investigate a technology that we expect and plan to fly on an unspecified future mission. Now, admittedly, the solar panels and the frame that I just talked about were a little odd because we do have a designated mission, but I really think of them as being open source projects with our first customer being golf. These, on the other hand, are really somewhat open-ended in the sense that we don't yet have specified payloads or specified satellites that they'll play on. So I'm going to talk about each of these individually. Starting with the top one, a slow scan TV payload. We have an initiative with Frank Karnauskas, who I think has just stepped out of the room. One of his opportunities, one of the things he pursues is the engagement of youth, like youth type initiatives, and he has recognized or specified that there's a lot of interest in folks receiving pictures from space. Even if they're not live pictures, just receiving pictures from space like you might find on the ISS. So to that end, one of the things that Frank has chartered his brethren in engineering to do is to build a slow scan TV payload. Our progress on that to date has been driven mostly by Will, our volunteer here on the third row. And his primary focus right now is really taking the slow scan TV software that we've really had some good success with on the CubeSat simulator, and taking that and porting it to our flight platform, specifically the TMS 570. So it's the first step down a path of getting a slow scan TV payload by getting the software running on the platform that we actually fly. The radios, PAs, and the filters and all that's a little bit unknown. I think at the moment I've sort of suggested that we just use a D to A to just pump a pin with the necessary modulated signal for slow scan TV just to get something into the ether. So more of a bit banging approach than anything scientific at this point. But that's because we're focusing on the algorithm. Pause. Questions? Yes, Bill. We don't have a mic. We do have a mic.
Could that SSTV payload be combined with a PACSAT payload?
Could that SSTV payload be combined? And I'm still repeating the question even though you have a mic. Yes, there's no reason it could not, in fact. There's obviously some integration points. You're using the AX5043 for the radio chip for the moment. We've struggled a little bit figuring out how to pump FM modulated audio through that, but I think it can be done on the AX5043. But we haven't driven down that far yet. But could we use yours? The answer is very plausibly. Moving on. SDR-B, formerly called SDR Plan B, we talked about that earlier. Ray Roberge and Rich Gopstein have been working on the SDR-B. Ray's been working primarily on the PCB layout and design and the multi-layer board routing. Rich has been really starting on the Linux aspects of that. Again, as Jerry noted, that's an E310 replacement in a lot of ways. That's in a CubeSat footprint format, which will make it give us a microwave payload that will be much more convenient to fly in a CubeSat than what we're currently flying in the commercial board. I'm going to move a little quicker and then maybe hold some questions, but feel free. The FM transponder is an open, kind of a green field that I just kind of threw out there. Andrew Robinson was here. I think I see him over there. is my engineering volunteer that's been taking lead on that. I left this one relatively greenfield when I said, I need a new FM transponder. And I stopped there. I didn't specify that we wanted to rebuild the Fox one. I didn't specify that I wanted discrete. I didn't specify that I wanted SDR. I was going to leave that up to the volunteer to pursue something of technical challenge and interest. It looks like we're heading down the SDR path right now, but there's still questions to be answered even there. That Andrew is currently doing a trade study on what is the initial prototype platform going to look like for development, and I do specify prototype at that point. So we are starting to make progress on that, but it's in the early stages for sure. I will not talk much about PACSAT because I think we have a whole PACSAT presentation coming up here, but that is another project under the Ascent umbrella. And this also is a good example of a fairly independent project. We have a very dedicated, very talented, and very, what's the right term, excited, I guess. I'm not using the quite right word there, but team that's really engaged on the PACSAT project, and they're enthused about it, and they're really bought into it. So they've been running independently. I provide some oversight as AVPE. I exert budget control mostly, but the technical approaches are largely theirs to solve. So very exciting as well. We'll keep going for a few minutes. Can I go long, or am I stopping when I stop? I've got a little more time. So at that point, I am going to pause and answer questions, but I will not answer questions about PACSAT because I would like Bill and his team to answer those when they present next, and they are next. So do we have any questions? Or oftentimes in this room, I get more suggestions than I have questions, and that's okay. Any questions about SDRB or the FM transponder before I continue? No? All right. I did talk a little bit about the youth initiative when I was talking about the SSTV payload as being a possible payload to fly in support of the youth initiative. There's another aspect that I'm not going to do justice to when I describe it, but it's basically a ground-based radio transmitter that students can receive on the ground, and the payload of that is going to contain a series of environmental sensors. The idea is to really give youth an opportunity to work in the STEM field, be able to build and receive actual environmental signals from payloads that are developed by us and deployed in major markets. And again, I'm not sure I'm doing that justice, but I hope, Frank, you're talking about that more tomorrow. What time? Tomorrow morning. I heard tomorrow morning. I'm going to run with that. But to that end, the volunteer who's doing that, Mr. Joseph DeVerde, is primarily taking lead on the KidSat environmental sensor, but he actually took that idea and decided to take it even further. He works in the chemical space, I'm going to say, and I'm going to get that wrong too. So all the things I have wrong, somebody can write down and email me about later. But he does work in an educational setting, working a lot with physics and or chemicals and or exciting things like that. So he has peers that he has polled about what would we actually be able to fly in our satellite that would provide real scientific value to the scientific community and add to the knowledge of our world in terms of environmental sensors. So he started polling his colleagues and began putting together a series of requirements. The words multispectral keep getting thrown about, so I kind of have a sense we're going to be flying some multispectral imaging here at some point, even recognizing we have some NOAA considerations when we start flying sensors of that nature. GPS payload is another Ascent project that we're just spinning up that Joseph has expressed an interest, personal interest in. We had made the decision a couple of weeks ago that even though it would be interesting to fly a GPS payload on Gulf T, the technical and schedule risks exceeded the potential value of that. So I immediately was willing to take that under the Ascent program. So we are looking at building a GNSS payload that will be able to fly on future AMSAT satellites. You'll remember from my thruster presentation, one of the three legs of the stool we need in orbit is location information. And this will be the payload that allows us to acquire that. And last but not least, we had a volunteer, Tom Davis, who did a fantastic job of putting together the physical reaction wheel assembly, the wheels, the motors, the housings. What we don't yet have is the control electronics to spin those wheels under our command and control. Mr. Don Corrington has a wheel in his possession, has some prototype electronic hardware in his possession, and has begun working on that. Moving right along now, I will shift gears a little bit to talk about Fox Plus, which is another program, sister program to Golf. I won't spend a huge amount of time on this, but I'm happy to answer questions. Golf Plus is intended to be a faster, more rapid launch sequence to get amateur radio in space and keep it there. Launches 1 or 2 or 3 per year should not be absurd to think about, maybe even more. To do that, I had intended originally to leverage the Fox FM transponder, but as you may have heard me say, we actually had to take a step back and develop a new FM transponder, mostly because we had end-of-life parts that impacted our ability to do so. So I have now pivoted, to use that term, pivoted, to fly the linear transponder module instead. And even though we still have end-of-life parts on the LTM, and we have Leandra and Dave Hartram working very hard on that, we are slowly getting those boards manufactured. I have 3 ICR boards in my possession that are being exercised by Mike Moore, I think, and I'm preparing to assemble 3 LIHU boards any day now once I get my act together and kit the parts. And then the last piece, the transceiver piece, is the one that's probably my long pole right this second. Well, we have another volunteer whose name is escaping me, Burns, who's working on assembling the TXRX board right now. Dan Habecker? Dan Habecker, I think, if I'm saying his last name correctly, is doing a bang-up job in terms of building the next generation TX board, which I'll be leveraging. I'm hoping that I'll be able to start manufacturing those late this year. My plan is to develop 3 prototype boards. Once any one of those works, I'm going to go ahead and build an initial production run of 5 or so boards, and I'm throwing these numbers around rather loosely, I admit. But once I start confirming that those are going to function and getting those to our partners, I keep throwing around the number of 20. I want 20 LTMs on the shelf so that I can share them with people. There will be people that correctly point out that we don't exactly have a lot of flight heritage with this particular iteration, but I share with my partners very openly that this is a low flight heritage board at this point, although we do have some experience with various aspects of it, and we should be very careful about our ground testing to make sure that we exercise it on the ground. And I'm looking at you, Dr. Fevig. AMSAT is providing that. Yeah. Oh, I'm sorry. We are commercially purchasing several components. The frame, the electrical power system, the antenna system is coming from ISI Space, as is the solar panels. There's a little bitty bracket that you can't see, but the frame, EPS, and antenna are supposed to be here this week. I'm supposed to have 2 sets of hardware showing up at my home this week. I haven't received shipping notice yet, so I'm a little suspicious it won't quite arrive, but in talking to the vendor a couple of weeks ago, it's very, very close. I'm going to show some pictures, but I'm going to move relatively quickly. Antenna, power, LIHU, but I do have a physical LIHU over here too. Talk a little bit about futures projects on the horizon. It shouldn't shock you to know that I am interested in getting thrusters in our bag of tricks. That was my whole presentation earlier. But I'm also very interested in expanding our microwave capabilities. And to that end, I have an open project right now that hasn't been funded or even really authorized. But I think I could obtain that by simply asking the board for permission, and I would get a nod to support a microwave ground station. I also like to talk about future partnerships that engineering is engaging in, because we need to continue to expand our capabilities and our reach and our scope. Dr. Ron Fevig is joining us today from University of North Dakota. We've had some very good conversations with Dr. Fevig. We are going to be partnering on the Cape 4 mission, which Nick Pugh is involved in, wherever Nick went off to. There he is. To provide an LTM platform for flight on that mission. So we're feeling real good about that. We're working closely with Dr. Fevig to figure out how to partner with what I'm going to call a university lab environment that has an ongoing presence. One of the challenges you have in a university is continued graduation of your students. It's hard to keep a consistent flow of knowledge. So by partnering with somebody like Dr. Fevig and some long-term employees and professors and grad students, we hope to be able to maintain a long-standing relationship there. I also throw out Morehead State University on this slide. We don't have anything formal, so if you're seeing this in this room or on the internet, this is not an endorsement in any way, but we did have some very positive conversations when we were out at Morehead State University for the AstroCon, and we do think there are some opportunities to partner with Morehead in terms of projects and opportunities. We have one more slide which is being provided by Jerry here, and then I'm going to take a breath and a drink.
The last piece that I had was in regard to future opportunities, if you will. One of the things about trying to get higher in orbit is, of course, the orbital debris. There are some possibilities that are opening up as the industry opens up, and such are, for example, to be actually hosted on a platform that stays in orbit somewhere. And those missions are out there right now for various things. In that case, with regard to orbital debris, that's their key to be able to, take care of that paperwork, if you will, and we would not have to worry about it. So that is, and also in doing this, we wouldn't necessarily need an entire satellites around it. So the idea of going to the higher orbits, though, requires a little bit of thought at the bottom, depending on where we go right off, because we are going to be in those thermal and radiation environments, for example, that we're working with to try to mitigate with RTIHU and such. And so far, we've had a few opportunities come to us, but they are usually, as the industry is faster paced than our 6 full-time employees, a rather short timeline for what we can deliver, especially because we don't have anything specifically there. Oh, let's see. Actually, that's not a good slide, sorry.
That's one we're skipping.
There we go. Should we be prepared to go for that, such a thing like that? In other words, start projects for that? Heck yes. Should we have something on the shelf ready to go? And that is a question that depends on a lot of factors. LTM will lead the way on that linear transponder module to go wherever, keeping an eye out for what it does. And or another option would be that we just kind of hang out, and if something comes up, then we do something. And that would be that quicker production, for example, or maybe even something commercial in order to get a higher orbit bird before we advance there with the goal. That's all I had for now, and this is where later I think we'll have an opportunity for the engineering team members to come up, do a little talk, and you can ask them very specific questions about the various systems and such.
So, yeah, you can't tell I may have been a professor somewhere in my past, so there's no such thing as a short presentation. However, I've been generously given a few more minutes for questions, so maybe about 5 minutes. If you have any questions, please. Okay, I got 5 more minutes. Please, help me out here. There we have a question.
Yeah, Jonathan. So one question I had, one comment, I suppose, and question is the SDR-based FM transponder. Having worked through one in orbit, BY-70-1, the latency was kind of it confused the brain, which is obviously going to be a problem if we're doing any full duplex stuff in geostationary or higher orbits. But in terms of the FM transponder, are you what sort of latency do you think you can achieve with current technologies?
I'm going to pull that time-honored tradition of answering a question I know the answer to and ignoring the one I don't know the answer to. We do have some considerations to take into account on an SDR. Power requirement being the big one. They're not necessarily cheap on power. That is just one of many considerations. I'll admit I hadn't considered the processor latency in the middle of that as being an issue, so I honestly haven't investigated it, but that is something to consider going forward for sure. Other questions, please? We have another question. Hold on, sorry a second, sorry. I know.
Sorry, I'm not familiar. Can you say more about CAPE 4? You just put the acronym up there.
I can't, but will we be talking about CAPE 4 at all, Nick, at all? Okay, there will be a presentation tomorrow that mentions it. Sorry about that, I just don't know that much about it as a mission. Any other questions? We have one more. Okay, you're a volunteer, that worries me.
Yeah, I spend my day job in this industry, so I could probably come up with a lot of questions. But we're overall moving towards a lot of AI/ML stuff. Do you foresee or ever think about AMSAT getting into looking at leveraging AI/ML for future exploratory things?
Yeah. So AI and ML and that type of deep learning networks, that type of thing, is an interesting technology. Most of that artificial intelligence, machine learning. I mean, it's in the news a lot, but what it really typically means is very complex pattern matching networks is really what it turns into in practice. I can think of many opportunities where we might fly a payload on our satellite, not as a amateur radio radio payload, but as a experimental payload that might utilize that in terms of detecting of space environment, mineral effects, any number of things. So I could see leveraging it. I don't have any volunteers expressing interest, so I haven't seen a lot of activity in it right now. I have one more question if anybody would like to ask one more. Who wants to be my last question? Hold on, sorry, it's coming.
Oh, you could have heard me. With the FM transponder looking at using an SDR solution, what's the possibility of using that also as a next generation linear transponder module?
Huge opportunity. In fact, that's why I'm most excited about leveraging SDR technology for the FM transponder. While my charter was originally to develop an EasySat with an FM transponder on it, I'm not able to do that right now. But I'm chartering this FM project to meet that objective, but it would really make me happy if we're able to leverage it for a variety of other modulations and capabilities, including linears and digitals and experimental payloads. So yes, that is exactly why I'm interested in doing it as an SDR at this point in time. With that, I know I'm out of time. Thank you all very, very much. I appreciate it.
All right, thank you very much, Jonathan and Jerry. We really appreciate the update. Next up on our docket is the PACSAT update and demonstration by Mr. Bill Reed, the PACSAT project manager. So big round of applause, please.
Good afternoon. My name is Bill Reed, NX5R. I think this is the 5th AMSAT project I've worked on. But this is by far, in my mind, the most exciting. And if you look at what we present this afternoon and think about not only where we are, but where we could go with it, I think there are some really cool things out there. So let me start by giving you an overview of this first phase of the project. Okay, PACSAT is not a satellite. PACSAT is not a satellite, it's just a payload. But it is a single CubeSat card, 92 by 92, that performs these PACSAT functions. We're an Ascent project and we are 100% open source, so you can see everything we're doing by going out to GitHub. This is a concept drawing that we started with back in July of 2022. And what it shows is what is on that 1U card. We have 4 AX5043s as the uplink. In front of that is preamps and filters and a splitter to get the signal to the 5 receivers. So we have 5 uplink receivers on 2 meters feeding into a 570. And for the downlink we have a single 5043. Yeah. And of course, we've got filters and a power amplifier for that. This is a very simple block diagram, and there's really a lot more to it than what's shown here. This is the software. Pretty simple concept. Just roll it together. Free RTOS, 3 state machines, a whole bunch of processes. So it's really, I'm being facetious, it's really quite complex, but too close. But you'll learn more about it here this afternoon. 4 uplinks. 4 uplinks, 5 5043s, 4 uplinks, and 1 downlink. Okay, we're 100% open source, and you can go to these URLs and look at all the docs for our project and all the source for our project. But the easy way to get there is just to go to github.com and search for PACSAT. These will come up. Like I said, I've worked on a number of AMSAT projects, but this one is really different. In the past, it's sort of been like herding cats, getting people assigned tasks and following what they're doing and make sure everything comes together. These 5 guys are incredible. Since 2022 until today, we are about 80% complete with this project, and I think that's incredible. Bob Strickland's going to speak to us in a few minutes about the circuit board he's done. He's doing the layout. Burns and Chris are both of the software guys, and Chris is going to give us a demonstration of a working PACSAT. We have a satellite over on that table. He has the ground station over here. The whole thing is working today. Corey has done a lot of the file system work for us. The file system is critical in order to store messages on the satellite. And Jim has done some of the hardware. He's developed the PACSAT prototype for us, and he's done a great job of cleaning up little things for us. So this is an incredible team. Kudos to the whole team. They have basically built a whole PACSAT from July 2022 to today. Okay, I'm going to turn it over to Bob Strickland. While Bob is coming up, are there any high-level questions I could answer? Kip?
What does it do?
Aha, yes, of course.
I know the name, but I don't know what it
Yes,
does.
well, that's what Chris is going to show you. That's the whole point of the demo. Anybody else? Not only look at what Chris is going to demo, but think about other things that could be added on to that. Andrew.
Hey, Bill. What type of baud rates are you thinking about for this payload?
Initial baud rates are going to be 1,200 up on the 4 uplinks and 9,600 down.
Okay.
On our demo here, we're doing 9,600 up and down.
So the 1200 is AFSK, Bell 202, blah, blah, blah?
Yep.
Okay.
Yep. But it's programmable, and you can change it on the satellite in flight.
Is there any way to pass audio through the receiver and the transmitter?
This is a digital product.
Well,
digital.
That's not answering the question. I'll point out that on AO16, that capability was there, and it made a whole second life for the satellite. I'll also point out that UO14 started out as a PACSAT, and once the computer quit working in it for PACSAT purposes, it was used as an FM repeater. It's also very useful from a command standpoint, that if you have one uplink that's not working, you can pass audio through it and try to identify what the QRM is.
All I can say to that is that I think the hardware design could support audio if it was programmed to do that. But this is really a payload. So if there's also an audio capability, it would be the rest of the satellite. Now there is a link to the IHU, and so we will probably be downlinking. Yeah.
Based on 30 years of flying PACSATs already.
Okay. Bob Strickland.
Okay. I think that those comments are good and worth thinking about, but the problem is that we have moved forward with the technology and the chips that are being used here. In those earlier satellites, the transmitter and the receiver was all linear, so it was easier to do that sort of loop back function where you could run through the thing. But now the chips that we're using are so highly integrated that there's a lot of processing going on within the chip, and the data is being passed around through I2C bus or SPI bus. And so you could digitize voice or linear type signals and try to pass those around, but still everything's got to be functioning. And you're trying to do diagnostics. It sounds like your idea is, but it's worth keeping in mind. But this sort of is another block diagram similar to what Bill was talking about. We're coming in through a 2-meter antenna, and then we run that through a preamp, a filter, and then we divide that single antenna into a signal to feed into 4 different receivers that are going to go back into the processor. And then the processor does its job and sends a signal back out through a single antenna and through a single transmitter chip. So we do have 5 of these digitizing radio chips in there that are in the loop of the thing, so to speak. We have several voltages that are involved, and we have a pretty good chunk of memory because we're moving files up and down off of the satellite. The other functions are pretty much similar to what's typically required in a satellite. So I've done this PC board layout just in the standard footprint. It's a 6-layer board, and it's used or built with the KiCad open system. So if you want to install KiCad, go to the links that Bill talked about. You can download it and you can open it up and look at the actual layout, or you could grab a piece of it if you wanted to use it for something, for one of your own personal projects. But you can see the 4 receivers are over here, and then the transmitter's down in this area, and then there's an amplifier, a PA, and then this is a filter to be sure we're staying within our band or within the range of output that we want to be in frequency. And we got a bunch of stuff over here for power and things like that. And this is what the physical layout looks like in KiCad, which is pretty neat to be able to see the thing. I've got more work to do to try to get these packages lined up. Working with the manufacturer right now to try to build a few of these boards for us. There's about 300 parts on this board. Some of the earlier projects, we did them all ourselves. There weren't so many parts on the board, but these days it seems like you're cramming more stuff in, and it's a lot more difficult to hand build them. I'm pretty proficient with surface mount, and I've got all that kind of capability, but rather use pick and place for some of these parts that are so precision. But it's very similar to the other board too. A lot of this came from the work that Zach did. I just sort of took his stuff and pushed it around into what was needed here for this project. So any questions for me? Yes. We got a mic coming.
Is this compatible with the ACDS that we have on the Golf T, because it has that same interface? And so if we put it on Golf T, it would have to be up there just underneath the ACDS. Or this board. Oh,
well, the connectors.
That
yeah.
4 by, I can't remember what it is.
It's like a
header.
PC104. It's
The
called.
PC104 header.
And that's a
There's
format
also
that-
one on Golf T
Yeah.
for that
Okay,
gyroscope system.
Yeah, this is based on a document that Burns brought to our attention. We're very fortunate to have Burns helping us out. And I tried to follow that same document. All the connections on these pins on this connector try to follow the ones that were defined previously, although there's some extras that I've got now. There's stuff on there too that weren't needed on this board. So there's some overlap in there, but yes, I tried to move in that direction. But keep in mind, this is really a prototype development type board to see what we can do. Power's come up several times in here. I'm constantly thinking about how much current different chips require and trying to make decisions about how to do things to minimize that power, because we do have that limitation of whatever those solar cells produce, that's all we're going to have. So we may find out, for instance, in the long run, we can't support 4 receiver chips, maybe only 2. There's a lot of work that could be done by somebody about just understanding what the thresholds are of people that are in the community for being able to use a satellite. And can you do just a little bit more maybe if we did a little bit more power output, for instance, we'll open up more people that could work with the satellite. But these chips are also very versatile and can operate at many different frequencies and different baud rates and different modulation schemes. So lots of tests or learning can come out of this board in the long run for us. Any other question? One more
So
question.
I would assume then that the 4 receivers are so that you can switch or either have simultaneous uplinks to the satellite or on different frequencies, or are they switchable?
That's all correct. You could have all 4 simultaneously listening. They're going to be buffering their received data, and then they send an interrupt to the processor that they've got data to be processed. And they're really running relatively slow compared to what the capability is on the processor, although trying to slow it down, because if you run that processor slower, it uses less power. So yes, the answer is yes. Yes, sir.
Thanks. What's the frequency range of the receivers? And what's the
They'll
filter
go
set at?
up to, I think it's 850 megahertz, something like that.
And how far down do they go?
How far down?
Yeah.
They're going to go below 2 meters, and we want to do 2 meters. So.
Okay, and the filter is set at, what's the filter? Is it the digital setup or is it hard? What's the range on the filter?
I'm sorry, I couldn't hear your question.
What's the range on the filter?
Well, the filter's designed to be narrow band. You know, we haven't picked the exact frequencies we're going to use in the long run, but I can put different filters on these boards to accommodate testing.
Okay, all right, thank you.
Okay.
Not a question, but a comment. I'm the youth initiative guy, and I am so excited about this for engaging kids, because kids don't talk today, they text. Okay, and I working with students at the University of Arizona, I can't tell you how many times we've had them out in the field and they move from AOS to LOS, holding their handheld, waiting for an opening in the chatter. They feel rude, you know, trying to break in. But you sit these kids down with a tablet and some kind of sound interface to a handheld, they go crazy. I mean, we miss Bob Bernuga's PACSATs or APRS sets so much. The kids had so much fun with that. I can't wait to see this fly.
That's a real interesting comment, and it is interesting to kind of have perspective on the technology shifting like that and paying attention to it, flowing with it. That's good.
Burns, did you want to say something, or Burns Fisher? Burns Fisher is one of the software architects, and a lot of this stuff has been ported over from Gulf, so you'll see some similarities there.
Oh, geez, I don't have anything to say now. Thanks, Bill. Yeah, one of my goals in AMSAT, yeah, I know. One of my, I was on the radio at one point, you know, I know how to do microphones. One of my goals in AMSAT is to try to share software around a whole bunch of projects. We started out with Fox, and I admit that I should have gone back further to find software that was already written. But so we've got the Fox software. The Fox software was ported more or less and tweaked and amplified and so on to Golf. And what I really thought I could help with on PACSAT is to start out with the Golf software and use a lot of that same stuff. And I think we've done that. That's what I first started out doing, was taking the Golf software, tearing out all of the stuff that we didn't need, but leaving the operating system, leaving the drivers, leaving the way that the processes, tasks are set up, and all that sort of thing. And I think this has been pretty successful. Chris has been able to use it effectively. So that's what I was happy to be able to do. And I'd like to also, by the way, give credit to Eric Skoog for the documentation about what pins get used by what devices. That was another of my goals, is to try to bring Golf stuff into PACSAT, because most of the PACSAT people are pretty much PACSAT mostly. So I wanted to try to bring some golf stuff in and again, not reinvent the wheel. So I think we've been pretty successful with that, and that's one of the reasons that we were successful in making so much progress is because we only reinvented wheels that needed to be reinvented. So that's all I had to say. Any questions? Any questions software-wise? Okay, thanks.
Yes. And now I get to do something I've always wanted to do my whole life. I get to become a satellite. So watch me. I'm going to go over there and I'm going to launch in about 5 minutes. And this gentleman, Chris Thompson, is going to be the ground station and he's going to talk to me. So watch this.
All right. So I'm bravely going to try and do a live demo. I'm Chris Thompson, to a potentially skeptical audience from what I'm hearing so far as well. So I'm Chris Thompson. I'm G0KLA, although I now live in Canada, so I'm also VE2 TCP. Although we have the satellite running with my US call sign, which is AC2CZ. So I seem to be collecting call signs. Let me set the scene then a little bit. We have a satellite that is potentially orbiting the Earth, potentially it's orbiting the moon, maybe it's hardware sitting on the gateway. It's a store and forward device. We can store data in it. We can pull that data down later at any point. We can pull it down based on a set of parameters. You can think of it in some ways like an old-time bulletin board system, but it's not really like that, because a bulletin board you sort of log into and do things interactively. With this, we need to know what's on the satellite. So we have a ground station here. This is the ground station software. And how do I make it point? One of these buttons? Yeah. This area up here will contain a listing of everything that's on the satellite. We need to know sort of what's on the satellite so we can interact with it. And typically, you wouldn't interact with it during a pass. I mean, you can if you're sitting there at the radio, but typically, it will collect the information, and offline, you'll say things like, okay, I want to download these files. I want this data. And then it'll go and get that data for you. And in the bottom here, we'll see the interaction with the satellite. We'll see things that are going on. And the ground station we've got set up here, we've got a Kenwood D710 radio. So it's a full duplex, 2 meter, 70 centimeters radio. We've got a DigiRig sound card going into the laptop. So that's it in terms of the ground station. And we've got 2 meter and 70 centimeter sort of small dummy antennas. So Bill, if you plug in the satellite, we're going to see a couple of things happen. The satellite is going to come over the horizon, as it were, and the ground station, as soon as it hears the satellite, is going to request the directory, the list of contents on the satellite. It's going to send it a command, and it's going to get, hopefully, that list back. So if you can... AOS, yeah.
Quick one, Chris, you say it's going to request it, does it have to have a certain signal strength, or does it just start asking?
It has to decode the packet.
That's okay. Here goes.
So it gets a message, PB empty, and it gets a message open. So it tells it that the PACSAT broadcast is available for business. But it should have automatically, of course, transmitted the directory. Now, why didn't it do that? Live. Because it's a demo. It's supposed to request the directory. Bill will tell you this was all working earlier. Nah, it always says that. It's a Windows thing, I bet, because I just plugged it in just a second ago. So you can see that it's receiving. It's got the time packet. The time is correct. We just received telemetry, so we can see on the telemetry tab Well, it doesn't look like we received telemetry, does it? We received the time packet, but not the telemetry. Okay, 1 second. We're going to kill Direwolf and just, you know, if you tried restarting it, speakers USB sound card. It looks like it's correct. It's the playback that's not working. It's not 100%. Okay. This might have to be an offline demo for people to see. Let's just try once more. We're gonna cheat and just try this other version here. Okay. So that transmitted and got the directory, came down in a whole set of packets. You can see here. This is really just the mechanics of how it's working. It isn't really important to the user. We've got a list of headers, and it's just the headers. It's not the contents of any of the files. So it may collect tens or hundreds of files, however many files are sitting on the satellite. So we might offline decide that we want a certain file. So this file here looks interesting to us, maybe. That's the AMSAT bulletin. We can give that priority 1 to be downloaded. And on the next pass, or if you're still in a pass, it'll automatically start downloading that file. You don't have to be there for that to happen. That's just about a 13K file. It's coming down at 9600 bits per second. It's also a zipped file. Things are automatically compressed. And if we open it up, we can see that it is, in fact, the AMSAT bulletin. So we just got all this data from the satellite in about 20 seconds or so. Let's say we've got a file like this one here. This one pretends it's a satellite that's orbiting around the moon, and it's cached its data somewhere, perhaps in a system that's got better antennas pointing back towards Earth so that we can download it. And this was with partner 1, some university partner that's partnered with us maybe to get that data back. What they might want to do is just set up a rule to download that data. So I can set up an equation that says anything that's sent to call sign partner 1, which I better spell correctly, then I want to download that automatically. So it puts that rule in automatically. So that would have been downloaded as soon as that was available. On the next pass, if there's more files, that would get downloaded automatically. And you could then have a program that automatically processes that data. And this is just some, sorry, I got a program telling me to take a break. This is just some binary data. You can export that data. You can process that data however you want to. Lastly, it's a system where we can upload data. So that data perhaps got uploaded by another spacecraft, but we can also upload data from the ground. So I could, reply to this message here, and I won't reply and include it, although I could. I'll just keep it short. Great message, 7.3, Chris. And as soon as I click send, the ground station is going to connect to the satellite, and it logs in and connects a full connection, and it'll upload that file. And you can see that it says here in the abstract down below that it's a little difficult to read, but that it logged in and that it uploaded it in 2 packets, and it gets a data end, and it successfully uploaded that data. If we now again request the directory, then we find there's now one more header here, and if we were to download that with priority 1, then we'll find that file will come down as well. There's also another file here which is an image, so I'll mark that to be downloaded priority 2. So it'll download those as soon as it has availability to do that, and they come down. That one comes down pretty quickly. Just want to see if we got some of the telemetry. So we do have some telemetry here that's being broadcast. There's a couple different ways we can do telemetry. This is telemetry that is being sent all the time. Think of that as a sort of safe mode type telemetry. We can also store whole orbit data telemetry, experiment telemetry in files on the spacecraft and download them. This is telemetry that's being broadcast. So we can see, for example, the 4 receivers. Only one of them is operational. 3 of them are marked as off. I'm not using the full hardware board here. We're just using a prototype board with only 1 receiver. And we've got the transmitter. You can see the temperature on the computer, for example, and we can plot graphs of these and so forth. So that's pretty much it. Just downloading that last file, which is an image file. I'll open that up as soon as it finishes, which it has. And we can see that it's just a picture of the radio chips on our board. It comes down again in about 30, 40 seconds or so for a 25K image. So that could be a camera image. A larger file could come down over multiple orbits. It picks up seamlessly. If you miss data in the file, when it requests missed pieces, it knows exactly the holes in the file that are missing, and it only requests those holes in the file. So it's very, very efficient. And because it broadcasts it, many stations can receive it at the same time. People don't have to re-request the same data over and over, so it makes an efficient system. But
Is the underlying protocol still, is the underlying protocol still Harold's PACSAT protocol, or have you guys done something new and different?
The underlying protocol is still Harold's PACSAT protocol.
Awesome.
There's no reason why we can't enhance that in compatible ways, but it's exactly his protocol. The uplink is all FTL0 protocol. Just uses the uplink parts of that, which is, I think, was common for the PACSATs, historical PACSATs. Question at the back?
Chris, from a functionality perspective, how does this differ, or will it differ from FalconSat?
It's very similar to FalconSat. FalconSat was, a much bigger satellite. It was about this by this by this. Okay, I don't know what that is in size, but 1.5 feet square. This fits on one board, 10 centimeters square. So obviously you've got to add batteries and PA to that, but it's a miniaturization of the same sort of concept that you could then fly along with other experiment partners. But it's an ascent project, so make up your idea of what you think it might be useful for, because it could be useful for lots of things. Question? Oh, there's one over here first, Barry.
Yeah, I'm just wondering here. I'm confused. You said that it could transmit down a picture. Where are they getting the picture from?
Yeah, the picture can come from an onboard camera. The picture can be uploaded by another station. That other station could be another satellite, something which doesn't have the power to beam that picture all the way back to Earth.
Okay,
or it can be hams on the ground who are sharing images for fun if we wanted to do that as well.
It's just options. Basically a store and forward digital satellite.
Yeah, it's a data platform.
Okay, thank you.
Okay, I think I saw 2 here. I'm going to go first.
How much storage is planned to be on this?
Yeah, and what type? So we've prototyped it with MRAM, which we've found to be very reliable on the other satellites. I'm not an expert on exactly why it's reliable, but it's been very reliable. I think the initial design is to have 4 chips, and they can be sort of 4 megabytes each or so. But there's no reason why we couldn't potentially have more chips now if we wanted. I know that FalconSat had about 16 megabytes of RAM on a RAM disk, and that was pretty useful for storing images and data. We certainly would want several megabytes so that we could store pictures and images, and so that it's worthwhile getting things down over multiple passes. The prototype has hardly any RAM. Actually, it's quite useful to test things with a very small amount of RAM. So we've got, I think, 16 or 32K of RAM at the moment. You can test it filling up and hitting the extremities and so forth. Yeah, Barry.
Since you're using the D710, which is a packet radio dual band, are you using any of the features of the D710, or are you using a separate interface going into your computer?
Yeah, I'm using a DigiRig interface, so it's just a sound card interface. And I'm running that into Direwolf as the packet TNC on the ground station. So
So in terms of the radio, the D710's packet capability is really not needed, or could it be used if the user wanted to add it?
It's not needed. It could possibly be used. I have to think about that. You need, the ground station has to be able to connect either through a serial cable or through TCP to what it thinks is a KISS TNC. That's how the ground station is written. So.
Chris, what's the power consumption?
Don't know. I wrote the software, so I'll leave that to the hardware guys.
Any idea, Bill?
A lot of that depends probably on how much transmit power we have. That's probably what'll be the biggest thing. And we're running this demo at 9600 bits per second. If we run all the uplinks and downlinks at that, no doubt that'll consume more power still. The radio chips, by the way, do 125 kilobits per second, so there's nothing stopping us experimenting with faster
Bill,
speeds as well.
That's 150 milliamps at 3 volts, 3.3? 5, got it.
So do I understand correctly that there would be 4 different uplink frequencies in use? Is there any provision for the software to tell the ground station which of those are open so that it can be switched automatically?
Yeah. So the when it transmits, it says open A here. You can see that tells you that receiver A is open and available. And if there were 4, it would say open A, B, C, D. And if one of them wasn't there, that letter is missing. So that gives the ground station the opportunity to know which channels are open and available. And I forget whether I coded it so that it puts the call signs on there. Some of the PACSATs used to put the call sign on there as well, and some of them didn't. But yeah, the mechanism is there for the ground station to be able to work out what's a clear channel. Now, clearly, we then have to be able to retune your radio and so forth. And I'll admit, I did write the ground station, but that is not written. That code doesn't exist.
Chris, I think I know the answer to this. It's me. I just wanted to give you a chance to say it for Frank and all. If you're a kid and you want to send text messages to somebody around the world, you can. Am I correct that you can just say, okay, this is to certain call sign, and on the other side you can say, tell me all the messages that are for me?
Yeah, you can definitely set up a rule that says download all the messages that come from this particular call sign. If you're, exchanging lots of messages with somebody, you can do that. You can also, there's no reason why the digipeater wouldn't be on to just send APRS messages. FalconSat did that. It becomes a cross-band digipeater as well, so people who like to use APRS can use that in parallel with this type of solution. We haven't just enabled that functionality. I guess written the code for that functionality, but that's not the most complicated part of the satellite, so we would definitely have that envisaged. Yeah.
I saw SHA in the code, like SHA hashing. Are you using that for error correction just to make sure the file is intact?
So there's quite a few different ways that error detection is done. The SHA algorithm is for commanding. When we send commands, it does God, I'm going to get the name, an HMAC 256, which I think uses the SHA algorithm with a secret key, but it doesn't transmit the secret key. So that's how we do the commanding. For the file integrity, they have a checksum, and they have a checksum both for the header and for the body of the file. And those are used to tell you both whether you've got single event upsets in the file that have happened on the satellite, and also when a ground station uploads data that it's that it's good data before the satellite sort of commits it and puts it in the directory. And that's in addition to the fact that in theory, the channel is error-free, okay? Because it's got error correction and so forth, and retries when data is uploaded. Any other questions?
I have LOS here.
Yeah, LOS, you can unplug it. All right, thanks everybody.
All right. right, thank you very much to all the teams from PACSAT. I, for one, am incredibly enthusiastic, and I love seeing the demo. I thought it was excellent. Thank you very much. I'm going to have to get some more calls to compete with Chris here. The only one I've got is F/N0ZGO/P, but that's just me. At this time, we actually are going to, I think Jerry may have stepped out for a moment, but we were going to bring up all the engineers and just have a Q&A panel. For those of you who would like to stay around for that, please do. I think he's just going to be a few minutes. If not, we will be doing dinner on your own tonight from 5 to 7. At 7 p.m. tonight, there is the AMSAT reception and auction with cash bar available. And Frank, the location for that is? Okay, great. Yeah, so it's called The Social, and it's directly opposite of the bar, which is Whiskey Tango over here. The Social. There'll be something to nibble on with your drink. So, all right. Since Jerry's not here, I actually think that we should just close it out for today. We had a great set of presentations today. I personally thank all of the presenters, really. They were all excellent. And I think we've got more lined up for you tomorrow. With that, I think we're going to close it for today. Thank you again for attending, and we'll see you all tonight for The Social.